Alright, so we're on part 72 of our PAINT5D sprint, which isn't really much of a sprint anymore now, is it? Because it's more than half of the videos that I have done so far. 72, and we're on video, what, 140? Okay, it's not... Well, 70 is 70. What is that? 7 and 7 is 14, 140. Oh, so it's like roughly half, right? Like right now it is half, right? And as we do more and more videos, it's going to be more and more than half. But whatever, that happens. So, so right now we want to take this pattern here. This is a screenshot of zooming in to the texture memory in a very specific place, a very specific 32 by 32 chunk where PAINT5D variables is stored, right? So this is a screenshot with a little text overlay. And the pixels in the corner have been, we've zoomed into these pixels in the corner. There's 4 pixels in the corner, basically, and we've zoomed in on those. But it's not, you can see that in the corner, this red pixel got chopped in half, and the green pixel got chopped in half, and the blue pixel got chopped in half, right? All the pixels on the corners have been chopped. And I don't know why. And the way we're going to solve this problem is we're going to go write a test case that's going to emulate this scenario exactly, right? So we've done a whole bunch of close proxies for this kind of scenario, right? So like right over here, we have kind of like this kind of thing, and then zooming in, right? So this is the source, and here's the destination viewport. And then we did something similar over here. We did a whole bunch of like proxies of what was going on to try to get things to work. But we never really got anything to work. Hold on here. So now that I'm looking at this diagram later, I realize that this diagram is a little bit hard to understand. So I'm just going to go in here for a second and change this. Like all these brackets, I'm just going to say IG. Ignored corner. Maybe IC would make more sense. Oh, well, whatever. Okay, so let's try to simulate the situation on my right monitor, or on the right side of my screen. Let's try to simulate that situation over here, right? So, what we're gonna do, we can make a little diagram of what's going on first, maybe. And the input is like a 512 by 512 canvas, right? And we have these pixels that are kind of in the corners. And we would like to I don't know if drawing this out is the best way to go here. Oops. Well, let's just draw this out and think about it. Space, I don't know, dot, space, maybe, I don't know. Something to communicate that there's stuff between here. And then same thing with this. Let's add some spaces. And then right over here we can be like, might be a little bit easier with maybe like a little dash. Right, and so this right here, this region is the source, and the source is, 512. So source equals frag chords. I'll just call them frags because I think that'll be easier to understand what we're doing here. Okay, so it's source slash fragment coordinates, and it's like a 512 by 512 kind of thing going on here. And we might want to also denote here that this is 512 by 512, just because it is kind of a weird diagram where we're omitting a lot of the positions, right? So this is also 512. Okay. So, right here, if we diagonally, let's just diagonally number this. So let's say this is, you know, actually we can do 0, 0, and then we can do, you know, 1, 1. And then over here, we have 510, 510. And then over here we have like 511, 511, right? And so this is the coordinate space that we're mapping over. And in the end, we want to oh, hold on. It's not exactly. This would also be abridged. We want to go from like 0, 0 to we want to go from 0, 0 to like really want this to be 0, 0, and then we want this to be 31, 31. Right? Because we actually want to we want to render this area as on screen. This area is going to be, you know, a 32 by 32 chunk. And then over here, that means that instead of 511, 510, it's going to be 511 minus 31. What does that give us? That gives us 480. So this is going to be like 480 here. Okay. We could actually figure out what all the other coordinates are, right? So that means that right, these diagonals hit everything. These diagonals hit everything, so we all want to also do, you know, we also want to do the bottom left. We want to do this bottom left area, then we want to do this top right area as well. Okay. And we're going to map this to a fetch of a 32 by 32 area, right? So there's going to be like a and of that 32 by 32, so let's say we have a 32 by 32 here. I don't know exactly how I want to draw this. Let's say we have this and it's 32 by 32. Then the pixel up here, this first pixel, or actually not this first pixel, but the 4 pixels. Alright, so these 4 pixels, let's kind of zoom in here. So these 4 pixels right here, at the top of the 32 by 32 we want to render. Then we also want to get at these. Let's take this and kind of center it. Okay. So right here, when we're talking about mapping this out, this 0 and this 31, well, everything in this first cell is going to map to here, right? So, here, how do we say A, B, C, and D? Let's call this just A, B, C, and D for a second. So that way you can say, hey, this A, B, C, D section has to map to, you know, here. Oh. Has to map to here. Here. Right? And respectively the same thing for, you know, over here as well, right? But this is, you know, 0, 0, and this is 1, 1, right? And then over here is where we have 30 and 31, right? So over here is where we have 30 and 31. We've kind of distorted that because we don't really have enough room to write this out, so let's just draw it like this. Not the best diagram. It's not the best diagram, right? But we get the idea, right? So we can make a note of this, right? So we can just say, you know, at vid.iid, and it's video number 140, and the time here is, you know, 0 hours, 11 minutes, and let's say 11 seconds, just because I like that number. Okay. And this here is, if we want to know what we're mapping, we can take this imgur URL. Okay. Right. So we could put it right here. We could put it down here. Keep this as reference. And so this thing here that we're mapping, right, is this thing over on the left, right? That's the scenario that we're trying to emulate. And this right here, this region here, is, you know, 32 by 32. And the thing is that we don't have to. We're pretty sure that the problems with our math, we're fairly certain that the problems with our math don't have anything to do with the translation. So for this test set, we're not going to like make this selection rectangle origined somewhere besides 0, 0, and we're not going to make this origin somewhere besides 0, 0, because we're pretty sure that that is not at fault, and so we're not going to worry about that. So, okay. So now let's kind of set up the problem, right? Let's try to set up this problem and think about, well, what's going to be in the test table, right? So in this test table, it's going to be a little bit different. Table of unit test code. So, you know, int32, table of unit test code. I'm going to move this over here again. Okay, so the table of unit test code here, number of tests times number of columns, whatever that is, we don't know what that is yet. Okay, and we want to create a selection rectangle here, and then we want the expected. We want to cluster expected outputs, right? So if we have a selection rectangle over here, we want a cluster of expected outputs, etc. So we actually need not 4 tests, but more like 16 tests, right? 4, 4, 4, and 4 tests. So let's do that. So we're going to say that the first selection rectangle is let's just assume diagonalness, right? If we assume diagonalness, that'll also make this easier, right? So, well, that can't be true down here, though. So, we're going to have to go, you know, 0, 0, or 0, 0. How do I want to do this? 0, 0, and 31, 31. And the expected output when we map it, when we map this scenario, we're expecting the output is always, 0, 0, right? We're expecting it always to map to this pixel up here, right? So this is, this is minimum x, this is maximum x. Let's say x0, y0, how about that? Alright, so this is x0, y0. And then over here is, x1, y1. Right, so it's the lower bound. And then after we have that, we have the upper bounds. And we've already used x, right? You use x0 and x1. So what we're going to do is we're just going to say xy. We're going to do x, y, and then z and w, right? So z and w will be the destinations, right? So just to keep it kind of simple, we're just going to say, okay, well, z0, w0, so zw, right? Which just stands for x and y in the destination. And then after zw, whatever the hell is the w, we have, it's just a 1x1 rectangle, right? So, actually, we're trying to select, it's always going to map to the exact same pixel, right? So really, we don't need a range, right? We don't need a range for the output, right? Because dx, the problem we're trying to emulate, the problem we're trying to set up, doesn't have a range of outputs. It just has a very specific output. So this whole rectangular region, we're expecting it to map to pixel 0, 0 over here, right? So that's all we really need, right? So we can make a note of this, right? So this is, this region here is source, and then this right here is dest, right? So we're thinking about the order in which we're doing things. We got the source and the destination. So now we have a nice little table with the first test case. So let's just duplicate this. Let's put a comma up here so we don't forget, because we forget a lot. And instead of, so we already got this wrong, right? So we said 0 to 31, and we really want to say 0, 0 to 15, 15. Okay? And then this one is 16, 16 to 31, 31, right? So this is a 32 by 32 block, but there's 4 different pixels represented in it, right? So we want to target, we're targeting this, and then we're targeting this, right? So that's nice, but we should probably also go through and scan line ordering, target this, target this, target this, target this. I think that would make more sense. Alternatively, we could just say, hey, this is enough, because if the, well, actually, no, because we want to target every single pixel here, right? So, the output for here is going to be 1, 1, right? So now we need something where we're going to get, like, a 0, 1. And so to get 0, 1, we're going to go 0, 16. Right, the lower bound is 0, 16 here. And then the upper bound is going to be, on the x-axis is going to be 31. But on the lower axis here, it's going to be 15, right? So we're selecting this, right? So 0, sorry, that's not right. This is, oh, well, this is because we did the y here. This goes over here. X's and Y's, sometimes I get them mixed up and do stupid stuff. So this is 0, 16, right? So 0, 16, so that puts us like right here. And then we're going to map to 15, 31. So if you go 15, 31, we end up right here, right? So that's the selection rectangle for this. And that means that it's going to put us at 0, 1. So actually, no, it belongs here. It does belong here. So now we need to flip this. We need to flip these values, right? So let's paste this down here. And we just got to flip, right? So this is going to be 16 and 0. And so it is a little redundant where it's like, why do I have to do all this redundancy? But it's for a good cause. 31, 15. And then this is going to be over to the right, so it's going to be 1, 0. 1 on the X, 0 on the Y. So 0, 0. 1, 0, 0, 1, 1, 1, right? So we have all the different permutations. Excellent. So this right here is the top left, right? So you might want to make a note of that somewhere. Just say top left dot if we really want to think of it, we could think it as 0, 1, 2, 3, right? Top left TL cell 0, 1, 2, and 3, right? These are the respective cells that we're looking at. 0, 1, 2, and 3, right? So then what we're going to do is we're just going to copy the entire diagram here. But we got to make sure that when we paste this, we add this extra comma here. And we're just going to translate everything over, right? So all these numbers should be correct, but we just have to translate them over to this area over here, right? So for that, we just have to add, I don't know how much we have to add, but we know that whatever we're going to add, the ending number is going to end at 511, right? So since we know the extreme edge is going to be 511, we can take the highest number here, 31, and we can just say, okay, well, 511 minus 31 gives us what? It gives us 480. Okay, so if we take 31 plus 480, gives us 511. So if we plus 480, so TL plus 480, top left plus 480 gets us top right, right? So then everywhere in here, right, we can just start replacing things. And we have 4 different things we need to replace, right? So the easy one is the 0, right? The easy one is the 0. Well, actually, let's replace these corners first. The corners are kind of the easy thing, right? So it's 30 and 31 everywhere, right? So we just say, well, actually, it's only translated on the X. We're only translating on the X. We only care about when we're looking at the destinations, it's only the X that's getting translated, right? So this is 30 and 31, 30 and 31 on the X, right over here. But the Y range hasn't changed, right? So it's only the X range we're translating. So let's only look at the X's. Okay. So right here, let's just translate all this. So we have 480 and 480, right? Because we just added 480. And then 16 plus 480. So 16 plus 480 gives us 496. So this is, 496 and 496, right? So we're only translating on the X. And so that's kind of what we're expecting, right? That is what we're expecting. And let's just kind of finish this, right? So this is top right. Okay. So now down here, it's going to be the same thing, except we have to add to the different cells. So we're going to take the original locations, right? Because it's easier to just work with this, I think. Let's make sure this original is correct, though, right? So 0, 0 to 15, 15 is this. Then we're going to go over here. It's going to be 16, 0 to hold on. Oh. Hold on. 16, 0. Okay. This becomes 31. Over here, this one becomes 15. Does that make sense? Yeah, that does. Okay. 0, 16, right? So 0 and 16, because we're in the next cell. Then we go all the way to 15, not to 16, just to 15 on the X. And a 31 to fill it all out, okay? And then over here, 16, 16, right? So 16 and 16 is inside the first pixel of the last cell, and then the last pixel of the last cell. Okay, yeah, that looks good to me. I just want to make sure that is correct before I start cutting and pasting and kind of meticulously filling out these values, right? So this is now our bottom right cell. So bottom right cell. And we might want to copy this information here as well, right? So so the bottom right equals, you know, so actually the top left plus 480 gets the bottom right, right? Well, not everything, but, you know, you take the top left and you add a transformation to some of the axes, right? So for this, we just have to... Well, first of all, we haven't fixed this yet, right? So we fixed the axes for the lower bound, right? But we didn't fix the axis for the upper bound. So, right, so 15 plus 480 for a second. So we do 15 plus 480, we got 495. 495 and 495. And then 31 plus 480. So if we do 480, so 31 plus 480, right? 31 plus 480 is going to give us 511. Okay, right? All the way over. That makes sense. Okay. And does it still map here though? No, because this is, you know, 0, 0, 1, 0, 0, 1, 1, 0. Over here, we're all the way in the 30s everywhere, right? So we got 30 and oh, actually, no, this is 0, right? We haven't translated anything on the Y, so that's actually correct. So the Y's still match, these Y's still match the previous Y's, right? Because we only translated on the X, so that looks good. Okay, cool. So now let's take these numbers here that we copied from up here, and we just want to translate on... And are these all the same? No, these aren't the same. So we want to translate on the... I want to translate on the Y, right? So we're going to add 480 to everything. So we're going to go 480, 480, and this is like 496, I believe. So 16 plus 480 is 496, I think. Yeah, 496. So we're going to paste this here. Then we're going to paste this one here. Yep. So we have these and these. Okay, so now 15 plus 480, right? So 15 plus 480. What do we get here? 495. So we got 495 and 495 plus 31 plus 480. So 31 plus 480 And that's going to give us 511. Okay, so we're going to put a 511 in here. Okay, so we've translated everything on the y. And so now the destination y we need to translate, right? So for the destination, we should be able to, what? So it's, should be 30 and 31, right? So it's down here, it's the same kind of numbers because they're on the edge of that 30 by 30, 32 by 32 texture. So we should just be able to steal these. Well, actually, no, we can't steal them like this because this one's the 30. These are the 30s. And then these ones are 31, right? Because we're translating. Right, we're adding. Okay, so does that make sense, right? So this is the bottom right, and so that would be over here. And on the y, we're going to have 30 for these two and 31 for here. So 30 and then 31. So yes, that does make sense. Okay, cool. So now for the next thing, we just want to, we can steal this here. And to get the last coordinates, all we need to do is interlace. So this is the bottom right. This is the bottom right. This was the bottom left. I don't know why I said BR. So top left, top right, bottom left. Well, actually, hold on. Yeah, this is bottom left because we only translated on one of them, right? So top left, top right, bottom left, right? So the top right, we only translate on one axis to get there. The bottom left, we only translate on one axis to get there. And then the bottom right, however, we have to translate on both, right? So all these coordinates are based on the top left here. To get this, really all we need to do is we need to just take all of the higher numbers and we're good, right? So if we take all the higher numbers, we'll be good. So we can just steal all these numbers and paste them, all the higher numbers, which are kind of obvious because they're like 3 digits instead of 2. And if we steal these, we're going to get the offset on the 45, right? We're going to get that 45-degree offset. Okay. Okay, cool. So we're expecting this to be all the ranges, right? So when we use this selection rectangle here, we're going to expect when we use this selection rectangle, we expect the output coordinate to always be this. When we use this selection rectangle, we expect the output coordinate to always be this. This selection rectangle, we expect the output coordinate to always be this. This selection rectangle, we expect the output coordinate to always be this, right? So because we have that kind of setup, we can start writing the final problem, I guess. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 16 tests, right? So over here we can say define number of tests, and that's 16 of them, and then define number of columns, and there's 2, 4, 6. There's 6 columns. And then down here we can undef that at the bottom of the function, right? So undef. And we could probably get rid of this error thing for now. So for, test index equals 0, test index is less than or equal to the max index, and then test index plus plus. Okay. So the max index, int32 max index equals number of tests minus 1. Okay. Int32 test index equals, doesn't really matter. So we got the test index, we got the max index, right? And then we also need a base a base value, right? So int32 base, base offset to first element of test. Right, base element. So when we're in here, we know that we have, some type of variable equals the current test index. Well, actually, unit test code, table of unit test code with the base plus some type of offset. And there's 6 of them. Alright, there's 6 kind of groupings of information here. So 0, 1, 2, 3, 4, and 5. And we know that the base value, this base equals the test index times the stride. And the stride is going to be the number of columns, right? So the stride is this. So up here, number of columns, 6 elements. So this gives us the base address, and then we kind of offset correctly to get each piece of data. So what are these pieces of data? What are we going to call them? Well, we already named them this in the diagram, so we might as well kind of continue with the same exact naming scheme, so that when we're looking at the code and we're looking at the variables, we can reference the diagrams and be like, oh, that's what that is, right? So it makes sense to just name them exactly the same. So we got the minimum input range and the maximum input range. So we create a selection rectangle of ranges to scan over to that we want to all map to the destination X and destination Y. So we have a certain range of values here that should all map to the destination X and destination Y, right? So input range low bound, right? So this is the input range low bound. This is the high bound. This is the input range, actually, this is low bound X, this is low bound Y. I got that wrong. And this is high bound X and then high bound Y, right? And then here is, output, instead of an output range, this is output chord, right? So there's one output chord, right? So we map a range of values to one output chord with a X and Y value. Okay, so now that we have that, we can start to call our function, and right, we can set up the function call. So we have kind of this, so we can steal this. And we're going to set up the function call right down here. And we have source X, source Y. So there's also a loop in here, right? There's another loop, right? So, for sx equals x0, and then sx is less than or equal to x1, sx plus plus. And if we want to get proper scanline order, then x is going to be in the inner loop, and then y is going to be on the outer loop. So the y loop here, the source y, is right here. Right, so we got the y loops, we got the x loops. Okay, so to make this kind of decent, we're just going to say, int32 source x, int32 destination x. Oh, sorry, source x and source y. So source x, source y. Okay. Then we have all these different values that we haven't documented yet. So we have all these kind of things here, right? So let's take those and put them in here as well. So int32, and test table data. Right, so this is the test table data, and it's the it's this thing again, right? Right, so it's all the test table data, right? So we're just kind of repeating ourselves, and this is why it's like kind of like, does it make sense to declare and then use them, because now we have kind of like this extra fluffiness in the code, right? So it's like, is that actually what we want to do? Well, we already have it, so let's just go with it, right? So right, okay. So, right, so these values here, right, if we highlight them, right, we can see these values right here are coming from our test table, right? So we're using the test table with the data. So we're creating a table of unit test code, and each one of these rows is a different test, right? And we have 16 different tests total. So the number of tests is 16, and the number of columns for each test is 6, right? So this is like a, you could really think of this as like a SQL table that we're like loading into the code to run a whole bunch of tests, right? You could think of it like that. That would be a good way to think of it. So let's go down through here and figure out the rest of this test. So once we've extracted the values here from the test, we need to dive a little bit deeper and do another inner loop here, because we are expecting the source X and source Y range to loop over inclusively the X0, Y0, and the X1, Y1 range, right? So we're looping over a selection rectangle, and we're hoping that all the values map to these values, right? So we have a selection rectangle here, and then we're expecting the outputs to all map to a very specific pixel on a texture, right? That is the scenario we're trying to figure out here, or the scenario we're trying to emulate. So we can take this and say, okay, this is a source location, that's good. Did we declare that though? Yeah, we got source X, cool. We also need a int vec2, I think it's int vec2, yeah. And we're gonna call this DST for destination. Right, destination X and Y. I would use a dx dy, but the thing is that we're writing this function in a way where it can be used in GLSL code. Therefore, we cannot use output parameters, because output parameters require pointers, and pointers are not something we can get away with in GLSL code. So we have to write this C99 code. The prototype for this function needs to be compatible as GLSL code. So this input range is, for this data set, the input range and output range never changes, right? So we're going from a 512 by 512, and we're mapping to a 32 by 32. In the original problem over on my left monitor, this 32 by 32 section of pixels that we're rendering, it's like offset somewhere into the texture, but we don't care about that because we're fairly certain that the problem is not translation. We're fairly certain of that no matter where that 32 by 32 chunk of memory was, even if it was at the origin, we would still have a problem. So to simplify the problem, both these data sets are origined at 0, 0, because we're pretty sure that's not the problem, and we don't want to add more variables to the problem, right? We want to isolate the problem, right? So if these tests fail, we know that the failure is not due to translation, because we made the origins for both of these data sets 0, 0, right? So the translation would never affect what the output is. Okay, so now that we know this is 512, 512, 32 by 32, we can go down here and say, okay, well then this would be a 511, and this would be a 511, right? So the input range is this. We're going over this large input range that represents fragment coordinates on the screen, and we're going to output to a 31 by 31, right? So if we want to make a note of this, I don't know, I think that's good enough for us. We could make a note of this that say, you know, so I don't know if I want to make a note. I think this is kind of terse enough, but we could say, you know, 0, 511 for 512 by 512. And then we could say, like, 0 to 31 for, you know, 32 by 32. Right? Just to make sure that we know, because sometimes these numbers are kind of weird to look at, because you're like 511, you're expecting a power of 2. Same thing with 31, you might be expecting a power of 2, and that might be confusing. So make a little note here that, you know, it's an inclusive range, right? So we have to remember the 0th pixel counts as one of those slots, so you don't go 0 to 512, right? We go 0 to 511, and this encompasses all these pixels here, right? Okay, so now that we have the input range and the output range, and we have this destination, we know the expected output is dx dy right here, right? So for this set of values, we're going to iterate over a rectangular region, and for every single iteration of this loop, we expect the output to be equal to dx dy, and if it's not, then we have a serious problem. Also, I think it would be easier if we looped this twice, and for the first time, we only do one iteration of this loop, right? So we say, we take that top left corner, right? Now that's just going to make things more complicated for us. Let's not do that. Screw that. Okay, so if dst.x is not equal to dx, or dst.y is not equal to dy, okay, then we have a problem, right? So error. I don't really care what this is. I don't really care what this error message is, but I just want it to be unique enough for in the entire code base, right? So, sure, something like that. Just make sure it's unique enough, right? So we just have to make sure that this message is unique for the entire year, right? As long as we're clever enough or unique enough to make this message unique for 365 days in a row for the year 2021, then once we're in 2022, all the messages that we've tagged with 2021 will be in the clear, right? We'll know they'll never be identical messages. So I'm really hoping that this will just work out of the box and I won't have to do anything. But that's wishful thinking. Okay, cool. So this is about ready to run. Let's just make sure that it is indeed called up here, right? So make sure that oh boy, that's a lot of stuff. Yeah, it looks like, yeah, it's ready to run. It's being called right here. Specific case number 4, right? So SC1, SC2, SC3, and SC4 are like, they are pieces of test code modeled off of like specific scenarios. So we actually draw like little diagrams for the scenario and then try to test. And then this was the original test we rewrote that has like a whole bunch of values. It was our first attempt, and we already got all of this test code to pass, and all of this test code is passing, and we inserted this because what we're seeing on screen right here isn't quite correct. So because what I'm seeing over here on my left monitor doesn't look quite correct, I basically mocked up that situation in code over here, and we're going to run it, and we're going to see if it passes. Now, if it passes, that means that that if this passes, that I'm going to be like 99% certain that this function, rectangle source mapped to rectangle destination, I'm going to be 99% certain that that logic works, and the problem with these destination pixels being kind of offset is somewhere else in the code. So that's the assumption, right? So Let's /AAC2020.sh. I see, and now we have bots in our chat, huh? It's really weird that, oh, I guess the bots kind of just come into the chat and then they kind of leave, huh? Okay, so, what do we got here? It looks like some of my commentary, I can tell this was a comment. So maybe when I wrote my comments, I just kind of forgot what I was doing here for a second. So BR cell 0. Do I have like a backslash in my commentary somewhere? Because that can screw you over sometimes. Okay, that's just weird. Expected a closing bracket before numeric constant. Oh, that's, okay, I got it. It's right here. Okay, so all the commas are here, all the commas are here, all the commas are here. And then right here, let's just make this a little bit more explicit and just draw it like that. That way when I'm looking at this, I can just see, here's all the commas, right? They're all lined up right there, so I can easily account for them. I can say, hey, all my commas are where they belong, and explicitly right here, there's not supposed to be a comma, right? Because we're doing like a lax comma style. So if we do that, looks like everything's accounted for. Let's keep that visual space there, that's fine. Okay, let's try to run that again. And then, hey, how's it going? Yeah, so yeah, I saw your, well, I mean, you saw because in chat, but, yeah, your computer is pretty badass. It looks like almost looks like a transformer. Let me put this back up here. So today is just writing some test code, and then, we're just writing some test code, trying to get things working here. Okay, so we failed somewhere. Okay, so this test is failing. So what I'm doing here is you can take this image and look at it, and this image is supposed to. We're going over the screen in the game. We're going over like every single pixel on screen, and we're trying to like zoom into a 32 by 32 section of pixels on like a texture. And the reason is I'm trying to inspect the. Oh, that's still badass. But that thing's got to be really expensive. But yeah, I'm actually working on some, yeah. So I'm making like this texture inspector, right? So I can inspect the pixels on the texture, and what you're seeing over here on my left is almost an attempt that like it almost quite works, but these pixels in the corner, you can see that the green pixel is all the way there, but it's kind of like chopped off a little bit, right? And it's chopped off a little bit here. This is yesterday. This is yesterday. This is a screenshot from last night. This is last night, yeah. It's not today. This is a screenshot from last night. Oh, awesome. Cool. Awesome. Yeah, if you have similarity, right, then you kind of know what the heck I'm doing, and it makes more sense when you're looking at the code, right? But yeah, you see how these pixels are getting kind of chopped off, right? So, a neural network, oh geez, that's some intense stuff. Yeah, like a machine. Yeah, so like, it'd be cool to like do some machine learning for, so right here, you're trying to make a neural network, which is machine learning, right? But yeah, it'd be cool. I think it'd be cool to like do something where you use some machine learning to try to generate art assets, because I say there's like no easy like create art button that you can code, and that's mostly true until you get into something like machine learning, right? But for machine learning, you need a big, huge data set, right? The only reason that a human being can like create like art really easily, that's really hard to code when you're like trying to write. If you try to write code to make art, it always turns out crappy, or at least in my experience. And the only reason a human can do it is because they actually have a very large data set already encoded into their brain, right? So, like when I'm drawing weird abstract patterns, right, I'm relying on like years and years of input, right? So if you could do some machine learning and pipe in a huge data set to help it train it make art, well, that is kind of scary, right? Because we're getting to the point where people say, oh, you can't replace artists and you can't replace programmers, and we're going to get to the point where all of us, we're all going to be replaceable, and I don't think it's going to lead to a utopia. I think, well, yeah, I think it's going to get scary. It's going to get scary. It's going to be like a... I think the robots are going to slowly replace us. I think we're going to get like androids that look exactly like humans, and they're going to be a lot smarter than us, so they're going to beat us in all the job interviews, and so then all the human beings are going to end up like homeless and on the streets, and then they're all going to die. We're all going to die, and then we're just going to be replaced by robots. We're never going to know like how many of us are actually still around because they look identical to us, right? And like if I'm an employer, do I want the you know, average intelligence person, or do I want this super smart robot, right? And then also it's illegal to do IQ tests in hiring, but yep. I feel like this is actually more plausible than Alex Jones stuff, but I do find Alex Jones kind of amusing and absurd. Though when I was like a middle schooler, some of the stuff Alex Jones said was like it seemed more plausible, because like, you know, I think you don't have as much experience to like know what's like plausible and what's not plausible. Because I when I was like in when I was in middle school, like I did a lot of science and math, but then I also read like occult books and conspiracy theory books. So like it's like that could have done some weird things to my brain. Okay, anyway, so this test is failing, so we're gonna need some output to be like, okay, what the hell is going on, right? So we want to know what's important. What's the most important thing we want to know? Well, we want to know what the test index is, right? So we want to know what test index we're failing on. That's the most important thing, right? Also, I know we kind of already did this code somewhere else, so we should be able to just steal it from some other test, right? I don't feel like writing this all over again, right? So this big chunk of stuff is kind of all the stuff we need. Or actually, no, this isn't quite it. This is slightly different. Okay, let's just go back up here for a second. Sometimes when you look for a shortcut, you just spend more time looking for a shortcut instead of biting the bullet and just, you know, doing the work. So let's just type this out. So we want the test index. We want to know what SX and SY are, right? So the source, we want to know the source locations, right? And we already know for all tests we're mapping from a 512 to 512 to a 32 by 32. We already know that, so we don't have to. We're good there. We're good there. We don't have to print that off. It's the same for every single test. So SX, SY, and then the we actually want to know what the actual output is, right? So we know they don't match, but what are we expecting and what are we getting, right? So let's take this and say, okay, well, what we're expecting is this dx and dy, right, for destination x, destination y. So we have the source coordinate, and we're expecting to get it transformed to this destination coordinate, but instead we got this other thing, right? So what we could do is we could say, this is expected, right? This is expected dx. This is, you know, the input sx, sy, and this is the input test index. So we have these inputs. Okay, then we have the expecteds, and then we have the what we actually got, right? So I like to say got rather than actual, just because, I don't know, I abbreviate everything in terms of 3 letters, and got just seems better than actual, right? Actor, actuator, got, yeah, I don't know. It's just it's less ambiguous 3 letters to use got rather than actual. So this is expected, this is actual, the gotten values, right? So now we actually have to change this though. So we have to say, well, the gotten value is dst, right? dst dot x and y. So let's put that in there before we forget about it. And then let's just kind of OCD, kind of like put some random characters in there, arbitrary characters, just so that these messages all line up nicely. And okay, cool. So that looks pretty good. The next thing I want to do is just go like just make a little thing where I can like make these little divider bars so I can see. So this section, this little list of things kind of like stands out as one group of data. And then also, I'm gonna make a little macro here. I'm gonna make like a little padding between these here. Yeah, and then right here I'm just going to say, you know, define pad, and I'm going to define pad as printf \n. And I just want to write it that way so it's a little bit less cluttery on def. Okay, so there we go. So now the idea is that we can get some insight as to what exactly is failing, right? So now this is actually the best case scenario, I think, that once we're certain that the values we're using are failing, because we want to make sure that the failure is because the code is wrong, not the test, right? So right now it could be that the test code is wrong, right? Maybe we didn't fill out this table correctly, right? So we need to rule that out first, and then once we've ruled that out, we can go on to like other possibilities. Okay, so the test index is 0, so oh boy, failing on the first test. So okay, and we see that sx and sy are they're not 0, right? So right, we started off at 0, 0. And then we're going through the range. This is the top left, and this is the bottom right of the selection rectangle here. And so Sx is somewhere within that selection rectangle. Right now it's at 9, 0. And that actually looks about right for this failure here, right? So if you look at this failure, if we zoom in here, this is supposed to be rendered as 32 by 32. And we're only getting like half of this, right? So we're getting like 8 pixels rather than 16 right here. Like each one of these blocks should be rendered as 16 pixels, but that's not what we're getting here. So this would be about 8 pixels right here. And then on the 9th, we would end up in the green area where we don't want to be. We want this to still be red, but that's not what we're getting. And the test data is actually reporting back exactly that problem. So, so as far as I'm concerned, I think that now I don't know about all these other tests, right? There's still the possibility that I have written these tests improperly. But as far as this test, I think this test is correctly mocking up the situation, and it is giving me the exact failure that I would be expecting for what I'm seeing in my shader code. So we're expecting 0, 0, and instead we're getting 1, 0. So we're expecting to be taking this input coordinate and we're expecting it to map to pixel 0, 0 on the texture, but instead this coordinate seems to be mapping to pixel 1, 0 on the texture. And I know when I say pixel, right, I guess technically it's like texel 1, 0, but I don't know. I think anyone understands when I say pixel 1, 0 on a texture, that is more understandable than saying texel 1, 0 on a texture. It depends on how familiar you are with graphics programming. I like to speak in a way that is as simple as possible for whatever I'm doing. So as long as people can understand what I'm saying. So I'd say that that this situation is correctly mocking up the scenario, and it's getting the failure case that I would expect. So we're going to comment this out really quick because we want to make sure that all the other tests are still passing, right? And I also want to view the problem in real time, and then I want to think about like how the heck am I going to change this? How the heck am I going to fix this? Because I don't know. Like, I thought about the math pretty hard, but obviously not hard enough. So if we look at this, so we're zoomed in on this, like, texture, and this black area is 512 by 512, right? So in this red area, we're just saying the red area is kind of out of bounds, or I guess technically this is fuchsia. So it's like a magenta that is leaning towards red, so that's like fuchsia. So yeah, you see how these 4 pixels, there's 4 pixels here, there's 4 pixels here, 4 pixels here, and 4 pixels here, and they're marking the bounds of a 32 by 32 section in texture memory. And for some reason, these pixels are getting chopped, right? So the pixels should very squarely fit into what I'm rendering here, right? They should tangent the corners, right? So the red, green, and blue should tangent this corner here. The magenta, yellow, and white should tangent this corner. The dark red, dark blue, dark white should tangent this corner. And dark cyan, dark yellow, and dark white should tangent this corner here, right? But they're all kind of like, it seems like we're rendering from the center of the pixel, right? So there's some type of weird pixel center nonsense going on here. Right? And you wouldn't notice that if you were mapping from one set of pixels to another set of pixels and you weren't doing any zooming in, zooming out, you would never notice this, right? Because we're doing kind of a right? Like all these coordinates that you're seeing are kind of like sub-pixel coordinates that we're mapping onto the screen, right? And so the math, this is the thing with math, with shader code, right? Like you think that like geometry is like really easy, and you think like, oh, this is just really simple calculations, but then when you realize that if you're off by just 1 pixel, right? If you're just off by 1 in any capacity, then everything just kind of blows up on you. And imagine if instead of rendering pixels, what if this yellow block here was supposed to be like an entire block of like very important memory, right? Then an off by 1 would be like catastrophic, right? So it's like you got to make sure that those calculations, you got to be very careful with those off by 1 errors. It's like 90% of my time is like, oh, we're off by 1. Let's fix it, right? So this doesn't look like an off by 1 error, right? Because you see like we're missing a whole quarter, right? This is only a quarter of that red pixel, right? Only of a quarter of this yellow pixel. So it doesn't immediately look like an off by 1, but I guarantee that what we're looking at here is an off by 1 error. So all the other tests are passing, right? So we got all these tests that pass, this test pass, and then we still weren't seeing the correct thing in the viewport, right? We still weren't seeing the correct thing in the viewport, so I made one more test, and then we finally got a failure, right? So, well, we had some more failures as we were writing these tests, but it's kind of crazy that, we wrote all these tests, and it took this set of tests, before we even saw any type of, before we could pragmatically detect what was going wrong. We wrote all of these tests, and we wrote all of these tests, right? And, like, it's a lot of test code. So if we scroll down here, everything down here is test code, right? So these are all, like, little test tables, little test diagrams, and it's ridiculous, right? So this is the thing where, like, thank you all, Papa Pig. This is the thing where, like, yeah, so unfortunately, like, actually, it's more like a 50% plus of my code is test code, right? Because it's like, I don't know if you've ever done origami, but origami is a really good example, right? So, right, so if we're gonna make a huge code base, we need to write a lot of tests, because a little bug here, a little bug here, that seem kind of like maybe inconsequential, or they seem like minor bugs, right? Like a whole bunch of very, very minor bugs or very infrequent bugs, they'll start to collect, right, over time as the code base gets bigger and bigger. And pretty soon, you know, theoretically, I guess theoretically might be the right word, a large enough code base will have a catastrophic error if it has any errors, right? So, or at least that's kind of how I see it. I might be kind of full of crap here, but the idea is that you could have a code base where it's like almost perfect everywhere, but just because of the nature of it being so large, even the tiniest mistakes, they compound into something catastrophic. So we're going to try to avoid that by writing test code. So let's just keep on chugging away and trying to figure out what's going on. So I guess the next thing we want to do is we want to look at the code that's actually responsible for this. So this is the range code, the range mapping code. So we have this... this is the source X location, and this is the minimum. So this is, when we're talking about the source rectangle, we're trying to take a coordinate within one region, and then map it into a coordinate within another region, right? So it's kind of like if you were to try to make like a 3D Pong game, or try to like fake 3D graphics, you would do some type of coordinate mapping like this as well, where... right, if the rectangle is, let's say you have like a long rectilinear hallway, right? And you're, God, this might not make sense. Okay, so let's try to draw this out for a second. So if you were to do like a fake 3D Pong game, right? And you wanted to fake the 3D graphics, then you would... So I've made a game like this before. Actually, maybe we can just make a... Let's actually see if we can... Let's see if we can... I'm sure somebody else has programmed this before. Let's search for like a QBasic 3D Pong, right? So, and let's look for some videos. No videos, huh? Okay, well, it's pretty simple, and I programmed it in like high school long ago. It's weird how, like, you know, not everything's on the internet. You kind of think everything's on the internet until you start to search for something really specific, and you're like, oh, it's not actually on the internet. Okay, so I made like a 3D Pong game once, And like you just, it's a kind of it had a straight on perspective kind of thing going on. And so let's take this. Let's put this over here. Let's try to mirror this. Okay, so mirror that. That's not too bad. Could be better, though. Let's move this up. Okay, so you have kind of like this hallway. And for this rectangle, this is where the pong action is happening, right? But then as the ball goes, so the ball's like bouncing on this outer rectangle, right? But then the ball can also bounce on the z-axis, like in and out of the screen, right? And to mimic that, all we have to do is we have to remap. We have to figure out where the ball is in terms of percentage x, percentage y on this rectangle, and then we can map it to here when the ball is like going way back on the z, and then we'll get the proper kind of like simulated kind of fake 3D-ness, right? And so we're trying to do something like that. We're not trying to make a 3D Pong game, but I'm trying to explain the range mapping in like a typical like use case that might make sense. Also, hold on here. Language, settings, style configurator. Let's try Andale Mono. Okay, that lines up a little bit better. You know, I think I find the perfect programming font, and then when I try to like line up characters for like drawing some type of ASCII diagram, like it just fails on me, and I just have to switch fonts. So right, so as we're okay, then after I'm done drawing this, I will get back to what I was doing here. Okay, not the best example because this is not completely square way down here, but you get the idea where like if we want to know if this ball is bouncing between the edges of this hallway, and want to figure out, well, what is it going to look like when it goes further down the hallway, we just have to map the XY position on this big rectangle to the XY position on this very small rectangle, and then we get where it looks proper, right? We're not actually trying to do any perspective mapping, though. That's just like an example use case. So let's just go... let's go open up our hashtag documentation. Let's just go put this somewhere, because that actually took a while to do. So let's just name this hashtag Pong Hallway. I'm just going to put this in here, just so that next time I want to explain this, I don't want to have to take the time to, like, hash something out in ASCII. I'll make a note of like when this was. So at video IID 140. The time is 1 hour, 18 minutes, and 26 seconds. Let's say 32 seconds because I like powers of 2. Explaining range mapping using fake 3D Pong example. Okay, so we can close that. And we can close this. We can close this. And so, I don't really know what is wrong with this math. I know the expected behavior I want, but I don't really know how to solve this. So the idea is that we turn the source x coordinate into a percentage along path, right? The input percentage along path, right? So we zero out the coordinates so that they're both origined at, 0, 0. And then we take the percent, we take the coordinate, which starts at 0, and we divide by this, right? So perhaps we're off by 1 here, right? So maybe So if we were going 0 to... Well, SX1 is an inclusive coordinate, right? So SX can actually be equal to this, right? So, you know, SX can be 0. Let's say it's a 32 by 32 chunk that we're going through, right? So 0 to 31, right? Or the range is 0 to 31, and the value for SX can be 0 to 31, right? So we start off at 0 31s, and then we go all the way up to 31 31s, right? So we get a percentage. So that to me looks like the basic correct math here. It's just that for some reason we're like off by 1. And I don't know how we're going to fix that. I have no clue what's wrong here. Max possible zeroed out coordinate, so we'll take the dx, right? So here's the range, dx0, dx1, that's the destination output, right? So the min and max for the output, right? So this is like the x-axis of the output selection rectangle here. And we're just going to multiply that percentage by that range, but we're going to zero it out before we multiply by that, and then we're going to undo that zero out after we've calculated all of this right here. So that seems to me like the correct math. It's obviously like 99% correct. It's like 99% correct, except that it is it's failing us for the corners. Like it's like a corner case. It's like literally a corner case where things are failing. So now I know when I implemented rounding, the calculations actually got closer to correct. I think the problem is that, well, if you have like something at 0.5, is that supposed to map up or down, right? Is it the rounding? I know if I do a seal, the results look even worse. If I do a floor, the results look worse than that. Because I thought that maybe I went from seal to round and the results looked better. And so I'm like, okay, if I go seal to round, it looks better. How about round to floor? So I tried floor. Floor didn't work, so I was guessing around. And then we have this case up here, right? So all the mapping isn't completely linear, right? Because if the input range is a 1-by-1 selection, we don't know where anything maps anymore, right? Because if this minus this is 0, none of this math works, right? Because this is now a division by 0 here. So we had to make this case here. So this is already kind of ugly in the terms of how we programmed it anyways. So I don't know how to fix this. In fact, I'm going to probably have to take some time to just get some graph paper and map out the situation. Because this formula is obviously kind of like not quite correct, and I don't know how to make it correct. I'm gonna have to take a break and just get some graph paper and do this. And also, today is my MakerWorks day, so I have to go to the machine shop later at like 7. So it's almost 4, 5, 6, 7. That gets me 3 hours to get some files ready to cut on the laser cutter. And so I'm going to probably stop the stream and start a new stream where I'm going to do some OpenSCAD stuff, which is not related to what I'm doing right now. But I need to get some files ready. I have like these other projects, right? So I have this rendering engine project, then I have like some patents that I actually spent a lot of money on to just get filed. Yeah, machine shop, yeah. So yeah, I have some Here, let's pull that up, you know? So, let's commit what we have. Actually, hold on. Yeah, let's commit what we have, and then I'll show you what that's all about. So, because right now, I'm kind of stuck, and when I'm at the machine shop, it's mostly going to be, like, running jobs on the laser cutter, so there's going to be a lot of time for me to, like, think. And so I'll bring some, like, graph paper and try to think out these formulas, because right now I have no clue how to get this mapping to work correctly. So let's, I know if I do the math with, like, pixel centers, that's probably part of how to fix this. But let's just go commit what we have and say, clear. Oh, actually, before we close this, though, we want to go into the unit test code. And, oh, it's in a fragment shader common code. So this is, this file we're in is called fragcom for fragment shader common code, so it's like common utility functions. We want to make sure that when we run this, we get the failure state, so we want to make sure that when we start up this code base again, next time we come back to this code base and we try to run it, we want the test that's currently failing to, like, be obnoxious and kind of show us, hey, you have a problem here, you got to fix it. So we want to comment this test case back in so that next time we try to run this, we're going to get this error message and we know where we left off. So we want to know where we left off, so that's good. So let's do git status. Git add dot, git status. Git commit dash am. Okay, so I'll push this up to GitHub, and then I'll show you those. Designs. Okay, yeah. So, one more thing though. I have a lot of files open, so I know I keep on saying. But before we go here, context switching. The thing that sucks about having more than one project is that you have a context switching cost, right? So. Right, just the fact that now I can't keep all these editors open, right, because I gotta open up the editors for some other things, for some other projects. There is a cost to the context switch of having to go open up another project and get all the editors set up for the other project, right? Now, even though, so when you talk about Scrum, right, so Scrum philosophy kind of goes over the cost of context switching, and I totally believe that there's a cost to context switching because I'm incurring that cost right now. But I'm just making a save state here. So I'm just making a save state of, like, all the things that I had thought were important to have open at the moment, right? So we're going to take this, and we're just going to go into our shortcuts, or we could... No, let's go into the AutoHotkey folder. And we have a shortcuts file, shortcut files. It's AA2. It's AAC 2020 specifically. We have openers. And let's just call this save states. Do you want it to be a save state or a to-do? I don't know, maybe to-do makes more sense, right? Because it's 2021-02-17. Fix texture, fix ranged mapping. So that's what we're trying to do. We're trying to fix the range mapping. So we'll make this little shortcut in our shortcut files so that we can come back to it, right? So let's just say, you know, fix range mapping. To do 2021-02-17, right? And then invoke file contents, right? So we're going to take whatever contents are inside this file, and we're going to invoke it as, like, code, and that code is going to basically just open up all the files, right? So we have that for later. So now we can safely kind of, like, close everything and actually get into some of the patent stuff. So let's go look at that. So I was kind of afraid to show people this stuff, but you know what? I already have the patents, so let's go do it. So Okay, so let's go into the CBS folder. I think is where most of this stuff is going to be. And yeah, we have some images. Let's go through these images and kind of show you what's up. And then we can also go through some of the 3D models and things. Yeah, let's just open this up. So, because I'm trying to figure out how to do something that's going to be profitable and get something profitable done pretty soon, I am going to start taking more time to work on mechanical patents in the foreseeable future. Because, and why is this not working here? Hold on. My Windows picture viewer seems to have crashed on me here. Let me close some things. And get some more RAM here. I don't think the file is corrupted. Okay, yeah. So, okay. So yeah, let's just kind of go through what we got here. So the idea is it's kind of like, stereotypically, the first thing people kind of grab onto is they say Lego. And I've also seen somebody do something where they called it Lego plus IKEA. I would also kind of use that same analogy. The idea here is to make the building block. Eventually, I want to make this building block out of cast aluminum, so we can make like frames for like modular aluminum furniture, right? So let's just go through. So this, when I made this screenshot, you can see this little peg here isn't completely aligned. So this is actually assembled incorrectly, but oh well. But you get the idea of kind of how this fits together. So I made some like little simple designs. Like this was like supposed to be a tray for the table where you could clean underneath it, and then we could put all the like tea and coffee up here because my mom hates it when I store things on the counter. So the idea was to like make a little tray as like a little compromise because my mom's like, oh, I can't clean the counters if you're storing things on the counter, right? So how about like a little tray on stilts, right? That was the idea. So this is the first product I want to work on. So it's going to take a whole month to build this. It's going to take one whole month. And so I'm thinking that selling this for, and this isn't the whole thing here, right? This is just the frame. There's also a tabletop that needs to go on this, right? So this is the frame of this coffee table design made with these modular blocks. And we're going to cut these out of like some clear acrylic, and we're going to put like fairy lights inside of the frame so we can make the frame kind of like glow. And then we're going to make some like nice wood inserts for the top here. So you see how there's like these little cells here? We're going to like put some wood inserts into here to make like a flat wooden tabletop. And I'm going to sell this for somewhere around, I guess I don't want to say an exact price yet, but okay, you imagine that it takes me a whole month to build this, so the price tag is going to be somewhere in the thousands. Now, that might make it a little bit harder to sell, but it needs to be worth my time, so I'm going to sell it for something in the thousands. Right, so the idea is to sell it as kind of like designer furniture, and not only is it designer furniture, right, I have an art degree, but the actual parts that I'm making it with are patented. So, so right in here, right, we're gonna, after we've bolted this together, right, we're going to insert like a wooden panel on the top and bottom, and that wooden panel will have a way to put a bolt through the wooden panel, right? So there's going to be a wooden panel on both the bottom and top, right? And then we put a bolt in the center to clamp that panel into place, right? So there's going to be 3x3 panels on this setup to create the whole top of the coffee table, right? So the idea is that with modularity like this, is that we can make a very wide range of furniture, but we don't have to have much space for inventory because everything can kind of collapse down into a small amount of space, right? So I don't have much space in the basement. I mean, I have claimed like a decent quarter of the basement, but there's only so much space to like build this kind of stuff. So this is the project I'm going to work on. This was just to get an idea of like if I wanted to create a big slab of wood and put it on top, trying to like visualize how much room was going to be taken up. I think this slab, I forgot how big this slab was. I think this is like a 3-inch thick slab. I actually did make a big wooden slab, but right now my ability at like running the shopbot and making tool paths for that aren't quite up to snuff. But it would be nice to like do a version of this table with like a butcher block, like a giant butcher block top. So like make a whole bunch of different table designs that all take like the same exact size butcher block top. And I'm gonna work on that, but for now, I'm gonna do what I can I need to focus on what I can currently do, right? So there's like things that I would like ideally want to do, like, you know, in programming there's those things that are like your nice to haves, right? So a nice to have would be to mill out a big solid block of wood, right? So like take a whole bunch of 2x4s and glue them together to make a big slab of wood, right? And then mill out that slab of wood into a nice big butcher block rectangle, right? And then insert it right on the top of the table, right? That would be pretty awesome, but I have to focus on what I can currently do at the moment. So this is like a nice to have. So we're not going to do this version. I've already made one of these. I actually have 2 of them, and this takes like a whole week to make. So like, right, so every single different color you're seeing here is a different cross section of wood, right? So so this is laser cut, and then after I laser cut it, I have to meticulously like glue and clamp together these panels, right? Because all these panels are made of 2 pieces of wood, right? So after I kind of like assemble the whole thing, you know, it literally takes me a whole week to make one of these. Sometimes 2 weeks, if like right, like if the process does not go smoothly, which sometimes it doesn't, right? Sometimes you encounter little hiccups, like the wood you're cutting has too much moisture in it, so it takes like twice as long to cut on the laser cutter, and so like now what you thought was only going to take you 1 week ends up taking you 2 weeks. So I have made one of these, right? So right, so we're taking kind of those modular so let's go back here for a second. So these pieces here that are used to make the frame, I'm calling these like bones, right? And then we're mixing the bones with these kind of like panel designs here, right? And we use that to make these modular like milk crates. So I really like milk crates, but one of the problems of milk crates is you start to stack them on top of each other, and then you don't know what's in the other milk crate, or you can't get to the other things without like removing this stack of milk crates on the top. So this is kind of like a milk crate, but hybrid with a shelving unit, right? So you can stack a whole bunch of these things on top of each other, and you can still get at the contents. Then you have like a little safety railing. This blue part right here is a safety railing, so that you can like set things in here, and you know, if the shelf gets a little jostled, or if you're picking up this entire crate and you're trying to move it somewhere else, you don't have to worry about the contents falling out of the crate, because we have a little guardrail, right? So it's like a shelf mixed with a milk crate. So this is just a screenshot of kind of like the code mixed with the screenshot, just to like advertise. I thought it was just a cool juxtaposition, being like, hey, this is the kind of code I use to create this kind of thing, right? So over here, you'll see that if we go back and forth between here, nothing changes, right? The only thing that changes is here we have 1 long crate, right, a tall crate, and here we have 2 crates. So the idea is that you could fill an entire wall with these crates, and then if you ever get an oversized item, so let's say we have an item that does not fit within these cubby holes, right? Well, we can just modify 2 of our crates, and we can make it twice as tall, and now our oversized item can kind of fit inside the crate, right? So imagine like maybe most of your things are like little bottles of things, like maybe you got bottles of solvents, you got screws, you got nails, you got bolts, and then for whatever reason you need some bolt cutters, right? And bolt cutters aren't going to fit in here, so now you got bolt cutters that can fit into a crate like this, right? So it's like a very modular system where you can create like where everything is kind of like regularized, right, or normalized. So here I'm just trying to assemble some interesting things, not using too many parts. And then over here is a mold. So we're gonna, eventually what I would like to do is I'd like to take cross sections and bolt these cross sections together to create a mold out of steel. that I can then pour molten aluminum in. And actually, I think my girlfriend already bought me the quartz and steel. Hold on, I gotta get up and check for a second. Yeah, so I have like a $200 slab of steel behind me. It's like sitting right behind me, like literally right behind my chair. I have a $200 slab of steel, and it's like it's a steel that is designed to be good for it has like a lot of corrosion resistant properties, and it can be used for mold making. So the idea is to make a mold out of cross sections of steel, bolt those cross sections together, and then pour molten aluminum in it, right, to make like a permanent mold. That's the goal. Now, I'm hoping that, you know, molten aluminum doesn't get the steel so hot that it starts to like bend and distort, right, because I don't want my mold to distort. But that could be a serious concern, because as I have been melting down metal, I have been seeing that my iron crucible tongs have been getting a little bit distorted, right? They're getting bent around because they get so hot. So here's like laser cross sections for some of the parts. So just a whole bunch of screenshots of the part files that I'm using to create certain things. And so now I want to start printing off parts in a way where I can. So here's like here's a small prototype, right? So here's if I were to use a wooden tabletop, I would use I could put bolts in the middle here, and then the tabletop could have like little holes in it, like little locator holes, and this bolt would go into the wood of the tabletop. Also, if you notice that this logo might look kind of like the logo I've been using. So the logo that I have currently for my coding stream is actually the logo for the company I set up. So I just reuse that logo because I don't want to make more logos, right? It's just use the same logo and then see what it gets associated with. Will it be more associated with programming, or will it be more associated with the products I'm working on? So here's a slab of wood I made, right? So I took a whole bunch of 2x4s, glued them together, and the idea was originally to like make a simple product where I could take a whole bunch of pipes and put the pipes in together to make like a frame, right? And then put this big slab of wood in it. But then as I tried to do that, I realized, holy crap, I can't actually screw together pipes to make a box, because of right, to get that last pipe screwed in, you can't really do it. So imagine you have this pipe here, and then you have a pipe over here in the front, and you try to screw in the edges, right? Well, you can't really make that happen. Well, maybe you could. I don't know, it's very difficult. Well, maybe you could. Let me think about it. I guess you could, but you would have to be screwing in this side while you're screwing in this side at the exact same moment. Like, it's kind of difficult. So I kind of abandoned that idea. I guess it could be done. Yeah, but it's a lot harder to implement well than I thought it would be, to make like a table frame out of pipes. And it's also still kind of expensive, so it's like, well, if I'm gonna try to make a piece of furniture, I might as well go all the way and just use kind of my modular designs and try to get something going. So I abandoned this, right? So I did try to make something like this. So we milled this piece of wood, and then right. So the idea is that the pipe kind of fits in this groove, right? The thing I don't like about this design, though, is that it looks like two big slabs of wood, right? It looks like we have this top thing and then we have this thing, right? So like if we look at a cross section here, this looks like two slabs of wood. It looks like there's this top slab of wood, and then it looks like there's this bottom slab of wood. But it's actually one gigantic slab of wood, and I actually just milled here. I milled this in, or I chamfered really deeply in. because I chamfered in here, it looks like 2 slabs of wood. And you might be like, oh, okay, what's the problem with that? Okay, the problem is what if you made something out of solid gold, okay? But you alloyed that gold with like a little bit of like some type of chemical that made the gold look like rusted metal, right? So you took like a whole bunch of gold bars, and you put like a little pinch of some type of metal that when it reacted with the gold somehow, right? Gold is very hard to make a chemical reaction with. But let's say hypothetically, you took a whole bunch of gold and you just put a little pinch of a certain chemical in that gold, and all of a sudden your gold looks like rusted metal, okay? And then you make a piece of furniture out of that rusted metal, right? Okay, it doesn't matter that it's made with gold now because it doesn't look like it's made with gold, right? So it looks like trash. So we have a similar analogous thing going on here. This is made with one gigantic slab of wood, but it doesn't look like it was made with one gigantic slab of wood. So we have a problem where it's higher quality than it looks. When somebody looks at this, they're going to assume less quality than what actually went into that. So when we're thinking about the design, it's not enough to design for quality. We actually have to make sure that the design accurately communicates the quality that it has, right? So this is just like more parts. So these are like corner parts. I stamped these out on like the I cut these parts out of metal to experiment. So you notice these parts kind of have these like different corners here, and you might notice that these holes are kind of rounded. So these are kind of design differences for the water and the plasma cutter. And so now what I need to do is I need to figure out how I'm going to... Well, the very first thing I need to do is I have a plan for cutting out felt washers. So assembling this thing using acrylic pieces, the lock washers can really scrape into the plastic or into the acrylic and damage the parts. So I need to create lock washers, or not lock washers. I need to create some felt washers. And I'm also going to try to sell those felt washers, because felt washers can actually be quite expensive. So if we look at felt washers on the internet for a second, let's close this, or minimize this. So let's look at felt washers here. Oh, thank you. So yeah, let's look for felt washers. Let's go look for felt washers for a second and see how much do these mofos cost. Felt washers, I don't know, Amazon. So if we want to get a few felt washers on Amazon, come on, let's just go to Amazon. Yeah, thank you. So let's go look at felt washers. So I don't know why it's saying baby care, because it was an advertisement. Let's just go to Amazon, www.amazon.com. Let's go look up how much it costs to get some felt washers. Felt washers. I think that's how you spell felt. I don't know. So okay, $5.99. How many are there? $5.99. Right, little felt washers. 32 ounces. Okay, but how many are here? I don't really see how many are here, right? So we need to know how many there are, right? To get an idea how expensive these are. Okay, here we go. Now I don't know if felt has anti-corrosive properties to begin with, right? Because I know that when people are advertising things on Amazon, sometimes they say like really fancy stuff that makes it sound like better than it is, right? So, you know, anti-corrosion washers, you're like, oh crap, I want the anti-corrosion washers, right? Like I don't want the normal felt washers, I want the anti-corrosion washers. But you know, if I did enough research into the properties of felt, we might find that these anti-corrosion washers are they're just literally felt, right? There's nothing special about it. It's just that they advertise it kind of specially, right? But we have, but you know, maybe I'm wrong. So let's try to find some. Okay, here's some felt washers. So $5.99. How many are there here? Like, it's kind of crazy how many product listings. It's kind of crazy where like I'm looking through this stuff, and yeah, we have like one crappy picture, and okay, I have to make the assumption here, right? I don't see anywhere in this description. I don't know. This just really annoys me with buying things online. I don't see anywhere in this product description that's telling me that how many washers I'm buying, right? So like we know the weight of the package or whatnot, and we can make the assumption that we're gonna get like, you know, 12 washers, right? But I don't really know if that's true or not, right? Because I don't see, like, if there's 12 washers, then somewhere in that description you should at least say 12 washers. But let's assume that this is 12 washers for like $6. Okay, $12, 12 washers, $6. So that's like 50 cents a piece, right? So let's go look at some more felt washers. So everything I'm seeing is pretty expensive, right? So and also the felt washer size that I want is very specific. So I could try to order these, but I need a lot. Like the things I'm making take like a lot of pieces. So you know how I said that, like I said earlier, that to make this table design, it's going to take me a whole month to make this, right? It's going to take me a whole month. And you might look at this and be like, well, why would that take a whole month? Well, you got to realize that the individual parts here, there's like almost 300, like when you're looking at this, oh, scroll back here, there's almost 300 parts right here, right? So all these individual pieces, there's almost 300 parts. So there is like a lot of surface area on all of these parts, right? Because they got all these like little prongs all over the place. So this is like a lot of cutting time on the laser, right? To cut all these parts out, it's a ridiculous amount of time. Now, I don't have the $250,000 it would take to make like plastic injection molds, right? So we're gonna make it out of acrylic, because you know I'm trying to start something up here, so I don't have the manufacturing capacity to do this out of plastic. But yeah, there's just a lot of surface area here. There's a lot of parts, so it's going to take a lot of time. So why am I talking about a lot of parts? Well, you see all these little tiny holes on everything? Everywhere where you see a little tiny hole is where I'm going to have to screw in a bolt. So I've already made this prototype once. The prototype is currently in shambles because my grandfather hit it with his car, and then my mom hit it with this car because it was in the garage. And I guess no one can drive in my family, I guess. I mean, everybody says they can drive, but the number of car crashes would attest to something different about that. But yeah, everyone hit this prototype, so it's all in shambles right now. But it took me 4 hours to just assemble this. So after like all the time it took to cut all of this, it then takes like 4 hours to just assemble the frame, right? That's not even including the panels that need to go on the top, right? And the panels, so it already takes like so when I say it's going to take a month, it could take longer than a month, but I think it's going to take about a month to make this. But anyways, we need a lot of felt washers because we have a lot of bolts. So for every single part, right, I said there's about 300 parts, right? Well, if you look at this one part, we have 1, 2, 3, 4 places a bolt can go, right? So over here, 1, 2, 3 as well. We have some places where there's 4, but it would be probably reasonable to say that if there's 300 parts, then you have to take 300 parts and 4 bolts per part. Actually, no, because there's a part on each side, so it'd be like You take 300 parts, you divide by 2, because the parts are in sets of 2, right? So now we got 150, and for each part there's about 3 holes. So 150 and 150 is 300, plus another 150, that's 450. That's 450 bolts. Oh wait, but we want felt washers on each side, so 450 times 2 gets us to, what, 900? So, if I'm only getting, like... So, if I'm trying to buy these on Amazon for 50 cents a piece instead of manufacturing my own, right? Well, what, 900 times 0.5, what do we got there? $450, right? So, you know how I said that when I'm going to sell this, I'm going to sell it for something in the thousands of dollars. You might be like, well, that's crazy. But the retail cost of the felt washers alone is going to cost me about $450. So it's not like it's not an unreasonable price at all. So before I start selling this model, I'm probably going to have to like get more felt, and I have to figure out like, well, how long does it take to cut the felt, right? And figure out how much that's costing me, right? Because I'm renting out shop time to use the laser cutter. So what's the price per part to me to cut this, right? So I got to buy the felt, then I got to cut the felt, so I have to think about the machine time for cutting that. I have no clue how fast this is going to be, right? So let's actually go look at our project here. And we got like a lot of projects we've made in terms of like making projects here, right? And we have M for models, so let me open this up. So I think I have like a master list of when I made certain models. Oh, this is when I'm using this for doing push-ups, which is kind of stupid. Okay, so let me close this. So when you have like a big folder full of like a lot of designs you've made, you kind of lose track of what was made when, right? So we can go view and like do it by date, right? So we can sort by date. And that's going to help us a little bit to figure out what goes where. But that might not be the perfect order, right? So sometimes in my designs, I'll put like little notes as to when things were made. So what do we got here? So okay, so this was just a bolt design. So I made like a project for making bolts, so that I could accurately kind of like draft things out and account for the size of the bolts that I'm using and make sure that the math all works out correctly. Common box that. So I have no clue what some of this stuff is because it's been a while. Okay, yeah, so I know what this is. So this common box slat is for, if we go into, let's go into our Git, and I think I have a photos section. So let's go to my Git. Actually, I think I have a GP folder for Git photos. For mail, MISC, patent UPAT. So let's go in here for a second, see what's in here. Some of this stuff you may have already seen. Okay, so there's some scans. Oh, so Git paper. Okay, yeah, so some scans of some drawings and whatnot. PR, I have no clue what PR means anymore. Let's go look at it. I'm going to guess that stands for photo something or other. Oh yeah, so some old designs for some things. So some more geometric things. Initially, I wanted to use these parts and make like a giant trebuchet, like a giant, like I wanted to make like a one-story trebuchet out of modular parts that were cast out of aluminum, but that's kind of like a far future goal because I have to figure out how to like cast these out of aluminum first. But right, so this is kind of like a wheel design, right? So this is like a wheel prototype I was working on so that I could like make like some use these modular parts to make wheels. Because if I'm making a giant trebuchet, it needs to have wheels, and if I want to use all modular parts, how am I going to do that? So I was kind of playing with how I would make a wheel. So this is just me kind of taking screenshots of this because I threw this out. So after you make a lot of prototypes, you have to start throwing stuff out because it starts to take up a lot of space, and it's not like code where you can just be like, oh, I just need like a few more gig hard drive and I'm done, right? Like you got to actually have physical space for this stuff. So this panel right here is a panel for that wheel design. So this panel goes onto here, right? So you can see where these pegs are kind of standing out. So you would bolt the peg, you would bolt those panels onto there to create a full wheel. But yeah, this is just too ambitious for now, so we're not doing that. What else is in here? Let's go look in here for a second. MISC. What's in MISC? I don't think there's anything incriminating in MISC. Let's hope not. Oh, yeah, so you saw these two earlier, right? Oh, you didn't see this one. You saw this one, right? So if you look at the other side of my setup here, you'll notice a whole bunch of interesting things. So first of all, down here is a modular crate. So this is one of my patented designs, a modular crate. And this modular design actually started off like 5 years ago. I was trying to figure out how to like cut parts out of sheet metal to make like a modular way to make like rings. I wanted a modular way to make rings so that I could go dig a tunnel, right? I wanted to dig a tunnel, and one of the ways you dig a tunnel is you dig into the side of a hill and you just chisel off just a little bit of dirt, right? And then you insert a ring. Okay, and then after you insert that ring, you chisel out a little bit more dirt, and then you insert a ring. And you can keep on doing that, and you'll never have to worry about a tunnel collapse, because if the little ring of dirt that you chipped away collapses on you, it's like, oh no, a little bit of dirt fell on me, but it's not enough to bury you, right? So you gradually build the tunnel by inserting ring by ring. So I wanted a way to make like a metal ring by taking a whole bunch of modular parts and then just bolting them together to make a ring, and then insert that ring into a tunnel. So the idea is that, you know, eventually, in the future, I want like a hobbit house. Yeah, this is the basement, so I guess the basement is kind of like my lab. You could say that. But yeah, so I wanted to do something like that, because eventually, like, I want a hobbit house, because, okay, so property taxes are really high, right? So, like, I don't want to get too political, but I'm going to get a little bit political, but not political enough to get me canceled. You don't really own property, right? There's no way to own property on Earth, except for, like, in some, like, what is it? Somewhere in the Caribbean you can own property, and then somewhere else, like Liechtenstein is a very small country where you can own property, but there's very few places where you can actually own property, right? So when I mean actually own property, I mean you have to pay property tax, right? So you can't just buy the property and then just hang out on your property as a hermit and just totally detach from society, right? Somebody, if you are alive, somebody wants money from you, right? So you can't just claim some property and then just be like, leave me alone, right? People are going to want money from you. So if you have property, you have to pay rent on it, right? So now some people pay rent in the form of a landlord, and then some people, quote-unquote, own their land, but they still have to pay property tax on it, right? So the property tax on my grandfather's place is fairly expensive. It's like it's in the thousands per year. So if you have a big enough place, the property tax is more expensive than rent, right? So the idea is that eventually I'd like to have like a farm, right? Make a little farm, right? So try to get the tax discount from a farm so that you don't have to pay expensive property tax, and then like most of your living space should be like underground, because if you build underground and people don't know about it, then you're not going to get taxed on it, right? So, which shouldn't say that online because, this is hypothetical. Hypothetical. I don't have an underground layer. It's hypothetical if the NSA is listening. But right, so like I would like a way to like, because I do see there's scenarios that are very real scenarios where you can have somebody who's retired and that retired person could end up homeless because they don't have any income anymore, and now their house that they built on their own, right? Maybe they did the whole American dream thing, right? And they built their own house, and now they're retired, but now their house, right, ends up being in an expensive part of the neighborhood, right? So like my grandfather on my dad's side, he built his own house, and now that house is worth like millions of dollars because people started building mansions all around him, right? So, you know, like once upon a time when I think somewhere around Bloomfield Hills, so it wasn't like a rich neighborhood when he went there to build his house, but he built his house, and now all these mansions prop up around his house, and now his house is worth like millions of dollars. Okay, well, some people like would celebrate, oh look, oh my property value is through the roof. No, property value is not a good thing. Property value is a horrible thing because more property value means you have to pay more taxes, right? So like if I would rather have a nice house or a nice house in a place where the property values are low, so I don't get taxed through the roof on having something, you know, just to live, right? But yeah, so imagine like maybe you didn't make much money when you were not retired, and you built your own house because you built your own house to save money, and now a whole bunch of mansions pop up around you, and now you can't keep your house. You can't afford to keep the house you built because all these mansions are kind of like skyrocketing the property values, and now your property taxes are through the roof, and right. So I want to think about avoiding a situation like that in the future. So to avoid a situation like that in the future in America, I don't know where you're from, but in America, if I want to avoid that situation, the best strategy would be to start a farm, right? So start like a very small farm so that I can have a discount on the property tax, right? Where like, or I might not even be taxed at all, right? Like, or the tax is incredibly cheap, right? Start a farm and try to sell some stuff. So even if I break even, I'm still profiting because I don't have that negative income of the property tax, right? So make a small little farm and then build my living situation there. Another way to avoid problems would be, I don't know if you've heard the saying, you're either making money or you're losing money, right? So, and that's very true, right? If you have money in your bank account right now, you're losing money because inflation is slowly evaporating that money in the bank account, right? The interest from the money in the bank account is not enough to make up for inflation. So you can't just store money and be good. If you're not making money, you are losing money. So another way to not go broke would be to build a little coffee shop, right? And then have your living arrangements like on top of the coffee shop, right? So you have a piece of property that is bringing in revenue, right? So, but a lot of these are like far future goals because right now I don't have the resources to do that kind of stuff, right? But I need to think about how I'm going to do things in a way where I'm going to be okay in the future. Anyway, so this setup you're seeing here, right? So I got my little COVID mask, SARS mask. Technically, it's just a different version of SARS, right? So we could just call it a SARS mask, right? So the really high-grade masks that you can buy don't filter your exhaling, right? So if you see this blue around here and this blue around here, I took N95 medical masks and I cut them up, and then I duct taped them around the exhale valves. So the whole idea is that, you know, the reason why these kind of masks right here are not allowed in hospitals or not allowed in like other establishments is because they don't protect other people, right? You exhale through this, and the air that comes out is unfiltered. So it'll protect you, but it won't protect other people. So I took this mask and I kind of retrofitted it so that it could protect other people, right? And I wish that masks weren't totally political. But anyways, because right, like masks can be a political subject for some reason. But I like to be, I don't know, my political affiliation is what's ever factually correct. So masks help reduce the spread of SARS. Let's not get too much into the politics around that because there's a whole bunch of nonsense going on with that, right? So you see over here, you see this kind of stuff here, all this striation here? That is 3 tons of acrylic. Well, technically it's, 1.5 tons, because this is 1/2, right? The other half is somewhere else. But yeah, sitting right behind me. So my chair is somewhere between all of this acrylic and this workstation here, right? So this workstation is a whole bunch of zip-tied together shelving, right? So really nice quality shelving, actually. It's like the best, as far as I'm concerned, it's the best quality modular shelving you can buy. Right, so it has all these kind of like, it takes the like rods, and you put the rods in here, and then you have like little plastic couplings that you slide onto the rod at certain increments to make the shelf to your specifications for how you can space out the shelf how you want it, right? And it's a really good shelving unit, and I used to have a whole bunch of them when I lived in Seattle. Now I have like a worse shelving unit, but I'm not complaining. It gets the job done. Hold on, make sure my stepmom is in here. Okay, so my stepmom is not... So my stepmom kind of comes... So my stepmom sometimes comes on my channel. But yeah, she bought these new shelves for me, and I appreciate that she bought the shelves for me. But the quality is nowhere near the quality of the kind of shelving I have here. And I think she knows the difference in quality because she kept the other shelves that my dad used. But yeah, I don't want to sound like, ungrateful, because I do appreciate the shelves that she bought me, and they are working for what they need to be used for. It's just that I wish that they were a little bit higher quality. But they work for what I need them to work for. So anyways, yeah, that is my my setup, right? So now when you're looking down here at this like modular box I made, so like 5 years ago, maybe more than 5 years ago, right, I was trying to make modular parts for making a tunnel, and then I ended up stumbling upon, well, what happened was I made these modular parts designed to make tunnels. And then after I had made these parts, I was like, okay, well now I gotta like put it in like a badass box, right? Like, if I'm gonna sell this product, I need to put it in a badass box, right? And so then I'm like, okay, well how do I make like a, I don't want to glue things together, because I don't want to glue things together. So how do I like make a box with like sides without gluing together stuff? So like how do I laser cut a box and then not glue anything together and still make a box with like right angle corners, right? How do I make like a volumetric box with laser cut parts? So how do I take like a flat cross-sectional parts and make volumetric structures so that I can make like a nice box for storing these parts that I made, right? So I went on a quest to kind of figure that out, and as I went on that quest to figure that out, I stumbled upon like designs like this. And I'm like, hey, you know what? This design is actually better than the original product. Like, the packaging was better than the original product. So then I started working on patents for that kind of stuff, right? So one of my patents is already filed. The other one is patent pending. So the design down here you see is mixed with a hybrid of parts that are already patented and then some parts that I have already submitted the patent application for. So, so the box is hybrid, patented, and patent pending. So after I made this box, I was like, you know what? I really want to make something where I can make like a modular parts to make like a portable computer setup, right? Because like I have all these monitors, right? I have all these monitors. How to make a portable computer setup where I have like just this giant setup that I can kind of lug around and I can set it down on a table and I can open it up, right? So like the setup that you showed me on Discord, I wanted to make something like that, but I wanted to use like modular parts. And I tried a lot of different variations, but in the end, after trying a lot of different variations, I realized that making modular parts, it's just too clunky. No matter what I make in terms of modular parts, it's always too clunky. Like, I could probably make something by now, but it would be a lot clunkier than I wanted. So I realized that the parts that I've kind of made, these parts, you know, it started tunnels, then I went to packaging, then I went to let's make rigs to hold computer parts, and then I was like, you know what, this works very good for making milk crates and modular furniture. So that's kind of where I am right now, is trying to figure out how to make modular furniture. Okay, so let's see. What else is in my... So the for Dale and Tom. So Dale and Tom are the people who own the machine shop. And so I took a whole bunch of screenshots of things and did it on... put them on stream to show them, like, what I was working on. So, as a thank you, because, like, at Christmas, like, everyone... they're turning their shop from a non-profit to a for-profit. Because right now, a lot of people who go to the shop do end up starting up successful businesses and patenting things. The problem is that after they patent things and they have a business going, they no longer need the shop, right? So I said to them one time that, you know, okay, well, if I end up making a successful business, I would like to still, like, donate to the shop, right? To help keep the shop up, right? Thank you. So the bottom one is not stained and the top one is. And then because they're modular parts, I don't know if you can see down here, but there's little feet on the bottom crate. So the top crate and the bottom crate are not identical. The bottom crate has little feet that have been added to it so that it doesn't sit on the ground, right? We don't want to, you know, furniture has legs so that, you know, because the floor is dirty, right? So this bottom box is kind of sitting on stilts. But yeah, so I showed them the stuff I made. I'm like, you know what, if I were to be successful, I'd like to make donations, right? But as a non-profit, that doesn't really actually work. Or actually, is it the other way around? Hold on. They're either going from non-profit to for-profit. Okay, you know, actually, I got that wrong. I totally said the wrong thing. Hold on. I got that inverted. Oh. So right now, their for-profit company is not making any money. And what I would like to do is I'd like to be able to, like, make donations, right? Like, if I can get something that's actually going to make money, and I, like, make a successful company, then I want to be able to, like, just say, hey, I appreciate that, you know, without your shop and without, like, all your staff and all the tutorial classes, like, all the education that I've had from there, without any of that, I would not be where I am, right? Like, even though I'm not successful yet, right? I'm not successful yet. I have patents and things, and I made cool things, but I'm not successful yet, right? But if I become successful to the point where I'm generating a revenue, I'd like to show that thanks, right? Because the rent on their space is pretty expensive, right? Because they got, like, a warehouse near Ann Arbor, and warehouse space is not cheap. I think their rent is maybe... Yeah, I think their rent is like $6,000 per month. So they're not making a profit right now, right? So it's kind of like, you know, one of them is an engineer. Like, Dale is an engineer, and then Tom is a computer software guy. So he does, like, a lot of SQL. And I don't know what other thing he works on, but SQL seems to be, like, one of the main things he really does code for. And so, right, they both like, have obviously had, like, successful enough careers where they kind of get together and fork out the money for this kind of a thing, right? And so, you know, even though people will pay, like, a monthly subscription fee to go to their shop, it's still not enough to, like, cover, you know, rent, machine repair, all that kind of crazy stuff. So right now they made it as they made it as a for-profit. Sorry, I got that backwards. They did it as a for-profit, and they're going to switch to a non-profit so that people can have tax write-offs for donating money, right? So right now, if I want to just show my thanks and give them money, I mean, that'll still work, but it's not a tax write-off, right? So people would be more inclined to give donations if it were a nonprofit. And the thing with nonprofits is nonprofit is pretty deceptive. Nonprofit is pretty deceptive. I'm not saying that nonprofits are bad. It really depends on who's running the company. But nonprofits can be scams. I'm not saying they are a scam. I'm saying that the way the law works with nonprofits is ridiculous. Like a nonprofit, what makes a nonprofit just has to... A CEO So a CEO of a nonprofit could legally make multiple millions per year. Because to be a nonprofit, the only thing you have to do is make sure that your salary is reasonable for your industry. So if I make a nonprofit computer company, well, if the CEO of Apple is, making a few million every year, then at my nonprofit computer company, I can make a few million per year, right? The only thing I can't do as a nonprofit is make more profit than other people, right? But I just have to stay at or below what a for-profit company can do, right? So that's kind of messed up, right? Because I think that, as a nonprofit, you can pretty much make as much money as is needed, I think, in terms of, like, you can live very comfortably as a nonprofit, right? So they're changing from a nonprofit so that, the other thing about a nonprofit is, you make a donation to it and it's a tax write-off, right? So people are going to be more willing to give them money if it's a tax write-off, right? So yeah, I got these designs. So this is some metal I melted down. So I did this with, these are a whole bunch of cans I melted down. And yeah, so this is the first prototype. So this prototype no longer exists. Well, it kind of does, but it's been hit by a car multiple times. This prototype is half the thickness, right? So this prototype took me a long time to make. I didn't have all the parts I needed, so this part right here on the corners isn't exactly the right part, right? This is supposed to be a corner piece right here, but it's not because just because I had a limited number of parts, right? So if you look at how the bolts are kind of sticking out way out here like this, that's because this table is actually half the density that it should be. Because it's just a prototype to get the idea of, like, get a feel for what the product is going to be in the real world, right? I already have very accurate 3D models of this, but I wanted to know, like, well, what is it going to look like in the real world, right? And so this is to scale. This is a 2-scale coffee table, right? So this is a pretty small coffee table, right? Just a standard height coffee table, maybe a little bit taller than a normal coffee table. So a coffee table is anywhere between like 15 and 23 inches off the ground, depending. And this is the kind of like the smallest product I can make. The smallest useful product I can make, I think. So it's made with half the parts that the final version needs. So all these parts here are half the thickness that they should be, and that's why the bolts are kind of like sticking out here. All the parts are half the thickness, right? So the table is half the density because all the parts are half the thickness. So however long it took me to cut this, it's going to take me twice as long to cut the final table, right? And then once I make the final table, it's going to take me about 4 hours just to assemble all these parts, and then it's going to take me even more time just to make all the wooden panels that need to go into it. Also, the coloring here is off because I didn't have enough time to like take off like all the protective layering on all of this. So all the acrylic still has its protective layers, except for right here. You can see I took off the protective layer here. So the final table, I have to peel off the protective layer. And because there's going to be, what I say, around 300 parts, right? And it's double layered, right? So there's a protective layer on the top and bottom. So that's 600 peels I have to do. I have to peel off, and it's actually very difficult to peel off the protective layering because after you cut this, right, all these little grooves make it really hard to peel this. It's not like, oh, just grab it, peel it off. You have to grab it and slowly peel it off and very carefully like wiggle around the grooves so that you can peel off in one smooth motion. And in order to peel off in one smooth motion, you have to go very slow. If you go fast, if you try to rush the process, you end up tearing off only a portion of the protective coating, and in your effort to save time, you'll actually spend more time because now you have to like you have to start like digging your fingernails into there to like get off the rest of it. So this is what I need to make. I'm going to sell it for somewhere in the thousands. So I don't want to say an exact price tag right now, but, you know, just assume it's going to take me about a month to make this, right? So, you know, if you know, that is a reasonable price for the amount of effort that's going to go into this. I don't want to quote an exact price now. I do have, like, a rough price that I want to go with, but because I have not finished one of these yet, there's a whole bunch of things that might nickel and dime me, right? Like I said, in terms of just the felt washers that are going into this, there's $450 worth of felt washers in this design. So what are the other small little things that I'm forgetting about that are going to add to the cost of this, right? So obviously, you know, the idea was to make something like IKEA furniture, but the quality of this is going to be, like, much higher. Also, even though it is modular, and I can, you know, store these parts very compactly, it's not really friendly in terms of the IKEA build-it-yourself kind of a thing, because it takes a lot of time. Or at least I don't think so. I mean, I was thinking maybe what I could do is, say, sell unassembled versions, and maybe sell them for, like, cheaper. And so let people, like, assemble them on their own, and see if people, if there's a market for that. But right now I'm thinking that the market for this is kind of like high-end designer furniture. And when we're talking high-end furniture, when we're talking about selling to, like, very rich clients, they don't want to spend 4 hours assembling something like this, right? They want something kind of fancy as a status symbol that looks, like, really cool. So this is, like, a very unique piece of art, right? That no one else can duplicate because I have the patents on the actual parts. So it's like a one-of-a-kind, expensive piece of designer furniture. So yeah, the market I'm going after, I don't think is going to facilitate a do-it-yourself kind of thing. Now, maybe in the future I can make some do-it-yourself kits. But oh god, I'm being raided. Okay. Hello. So I was going over modular furniture. So what you're looking at right now is a prototype of a coffee table. And this is to scale. Some of the parts aren't correct because I was running out of parts. So this, like, 4-way part actually should be a corner. But this is the basic idea. And each one of these cells, each one of these holes here you see, we're going to put, like, wood panels into here. And we're going to clamp them in there to make a final coffee table. So the final goal is to, like, make a modular coffee table out of, like, cast aluminum parts to make, like, this, like, really sturdy industrial design. But right now, molding from aluminum is a little bit too difficult. So the first designs we're going to make out of acrylic. So I have 3 tons of acrylic behind me, and we're going to cut these parts and make a final version of what you're seeing here. So let's kind of, like, go over what's going on here. So these parts here, I have patents on them. So I filed some patents. One of the patents is already granted, and it's basically a patent to create these, like, designer building blocks that I can make out of any type of material. So wood, or I can mold them out of aluminum, or make them out of steel, or, you know, I could mold them out of a variety of materials, and I can use them to build furniture, right? So I call these, the name I call these right now, I just call them bolt bones, which, you know, bolt bones. So bolt bone, TM. So this is what I'm going to call it. I'm going to call this a bolt bone. And there's other modular designs. So there's, like, this modular crate here. So it's like a milk crate, but one of the problems with milk crates is that when you stack them, it's really hard to, like, get at what's inside of it, right? So if you stack a whole bunch of milk crates on top of each other, to get to the contents of the bottom milk crate, it's really hard, right? You got to, like, remove all the milk crates on top before you can get in there. So we have, like, a little guardrail here. So if we want to move this milk crate around, things don't kind of go out of here, right? Also, this design here is made out of modular parts, but there's a lot of parts in here. So this whole thing, it took about a month to cut all the parts. So I'm thinking that I don't think anyone would buy something like this for how much I would need to sell it for, because I would need to sell this for like multiple hundreds of dollars, probably like something around $300. Don't quote me there, but I would need to sell this for about $300 to make it worth my time. I don't think anyone would buy one of these for $300. However, if you stack like 4 of these on top of each other to make like a really artsy kind of shelving unit, now I think you have something where someone might actually spend like $2,000 on it, right? So the way that the value perception scales is not completely linear, right? So if one of these, so I think somebody might buy this for like maybe $50, right? But it's not enough for me to sell to make a profit. But if I stack, you know, 2 more, if I stack 3 more on top of each other, instead of selling it for 200, right? That would be the linear scaling. If this was 50 and I stack 3 more on top, right? That would linearly scale to $200. But the perception of value, I don't think scales linearly. That's my hypothesis. So yeah, just a whole bunch of 3D models. So with that crate you saw, it's designed so that we can make a whole wall of crates and stack them on top of each other. And then if we ever have an oversized item, we can just subdivide it, right? So we can take like a stack of crates on the wall, and if we end up with the oversized item, we can, you know, do this, and now we can put our bolt cutters, right? Maybe we have a whole bunch of bolts and nails and things, and then we have some oversized bolt cutters. For example, I do have bolt cutters. I like bolt cutters and like some stuff for like melting metal. So I have like smelting tongs, right? Those are really big, so I need to like, you know, open that up so I have enough room, right? So yeah, the nice thing about this with these 3D models is I take the actual part files that I cut on the laser, and I use those part files to generate the 3D models. So when I mess with the 3D models and I assemble this in 3D space, this is going to sound crazy, but I have a 100% success rate. Okay, well maybe like 95%, because sometimes I screw up, but it's pretty much 100%. Like once I model this stuff out in 3D, I am 100% confident that whatever comes off of that laser cutter is going to assemble into the final product, right? So I made this 3D model first before I ever even tried to make this, right? It just fit together perfectly after I had made the 3D model. So it's going to take a lot of time to get that going. And so I actually have to write, so at 7 I have some time reserved for the laser cutter. And I actually need to cut some felt washers. So we're actually going to write some code for that kind of a thing now. So the first thing I want to do here is I want to, before I even start making files, I want to start to make an index of what I made when I made it, because I'm starting to lose track of all of my files, right? I have a whole bunch of files and I'm starting to lose track of them. So if I go into the main file for this thing here, I'm just going to open this with Notepad here, if I can get this to open here. And sometimes when I make a part file, when I make a new design, at the comments at the top, I say what the previous model was. So the previous model I worked on was called this, right? The previous model for that was called this. The current model that I'm working on in this file is called Crate Box Shelves, and the next model is Tetra Spline Block. So what we're going to do is, so we've kind of created this kind of mental linked list in the code so that I could kind of keep track of what was made when. So what we're going to do is we're going to say older models near top. We need to start making a master index of this because it's getting out of hand. It's like, it's getting to the point where I've made like thousands upon thousands of individual SCAD files and hundreds of projects. So I'm starting to lose track of everything, right? So I find that a very helpful way to keep track of things is to linearize it, right? So keep like a master diary of like all of the code projects you've worked on in a linear order, right? And if you keep it in a linear order, you can use that episodic. You can use your episodic memory to help seek backwards and forwards through projects you've worked on in the past to figure out what you're looking for. You can be like, I made that about 2 years ago, so it's probably way down the list. Or I made that a few months ago, so it's probably somewhere near the top of the list, right? So we're going to do that, right? We're going to take this comment here, which is kind of a mental linked list, right? Because we have the current node, which is this file, and the next node, and then we go back and back here, right? So we have the correct chronological ordering in our comments here. And the next thing we want to do is we just want to get rid of these comments here, and we just want to say like model, and now we want to go find touch a spline block and see what the comments are in there, right? So I just want to figure out, I just want to get my bearings. I haven't been in this code base for quite a while, and I just want to get my bearings as to like where everything is. So let's go look for touch a spline block. So here's touch a spline block. Let's go in here and let's go open up the main file for this. So let's go open this with Notepad++, and here's touch a spline block, and we see another linked list kind of thing. So the current model. So the thing that's kind of bothering me here is current model. There's no next model. So crate box shelves, Gramps gazebo bomb. So this may be one of the last things I worked on, but I don't know for sure. But we can kind of work backwards as well, right? So triple latch flats. Let's go look. Let's go open that up, right? And also let's keep this one open. So let's keep this one open because it's either the last thing we worked on, or it is, or we just forgot to build that linked list. So let's kind of go through some things and start to build this list backwards, right? So we just want to list, so triple latch flats. Let's go in here. Let's look at this. Okay, so we have Gramps gazebo bones. So I was like trying to design some modular. I was trying to make some modular designs where I could like make instead of making furniture, make like large scale things like decks and porches and things. So here's triple latch flats, and here's some other things. So let's take these and let's put them here, right? So right. So you'll notice that I have a naming convention where the folder has a very long name, and then we abbreviate to like 3 letters, right? So the idea is that when I have a whole bunch of files open in my editor, I don't want them to be this long because it actually kind of like makes things really hard to work with when I have long file names. That is kind of a symptom of the fact that I use Notepad++ for everything. So, you know, the tools you use to create are going to affect the outcome for what things look like, right? So, yeah, that's just going to be yeah, it doesn't matter what your setup, different computer setup, different environment setup, that will affect the end result, right? We live in a deterministic universe. That's just the reality. Now, sometimes the end result, the effect on the end result may be more or less severe. Hey, how's it going? So I'm actually working on I'm working on mechanical patents today. So let me go show you. I'm kind of like building a master index of stuff. I'll give you like a quick screenshot since you just popped in here, and I know you haven't kind of seen this stuff before. So let me just go look up in here for a second and show you. I'm just gonna blaze through here really quick because I've already kind of covered this. So let's. I do not know why my photo viewer keeps on stalling on me here. Let me try to get this working here. Hold on. Let's close this. Or I would like to just press Control-Alt-Delete, but that will wreck the if I close, okay, let's just close. Okay, let's try to open that up again. Actually, crate box shelves. This is decent. Let's go in here. Let's just open up this stuff. So blah 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 blah. So I'm trying to work on a modular coffee table. There's a crate like this, some other stuff, some cool stuff. parts, some things, a whole bunch of stuff. Here's a mold design. This is a mold design for casting my parts out of aluminum. So the idea is that we cut a cross-section out of, where is the mold? We take these cross-sections and we water jet cut them out of steel, and then we bolt them together, and then we pour aluminum into the cavities. So these big holes are like funnels, and these funnels go through these smaller holes and then go into the part. And there's venting holes as well. So I've thought it out. And I have some very expensive, like, corrosion resistant steel behind me for this process. What else do we got in here? So here are some of the final products. So here's, like, one of my crates that I made, modular crate. And then here's, like, a little scaffolding design where you would put, like, panels in between these holes. And then over here we have the coffee table design that I want to work on and sell. So... also, I was thinking about making the coffee table out of, like, both steel and plastic parts. So we would use the steel to reinforce it to make it stronger, and then we would put the plastic parts on the outside. And I'm looking at that and seeing that is a, that could be a plausible way to do this, because the plasma cut steel just looks ugly as sin, right? It's not as accurate, right? You can see all this wobble here. It looks ugly. But if we put the steel beneath the clear acrylic, we could get like something where it's nice and sturdy because it has the steel underneath it, but then it has the acrylic on top to make all these edges nice and square on the outside, right? So here's two of my crates. So the bottom crate actually has like little legs on it. And here's some like ingots. But anyways, I gotta close this because I have my appointment at 7. It's like 6, so I have to get rolling here. So we're gonna take what we have here. So let's see, previous model. Okay, so we have this open. So we're gonna go find that file now. So let's go. We're building an index. So it's easy to lose track of what you did when, like when you have a whole bunch of projects. So I'm going through my projects, right? So here's a project. And I'm going to go into the main file for this project. And this is SCAD code. This is not C code. And inside the main project, sometimes I keep a list of what the previous thing I worked on here. So I see this says next model is mom drawer tray. And if I go over here, I see indeed mom drawer tray. Now, I don't see... Oh, previous model was Mogamir. So I'm going to take this. And I know that the thing that comes next, the thing that comes previously is this thing. So burr.scad. So it's Mogamir. I don't know what the exact, what the unabbreviated version of this is, so now I gotta go in here and try to find it. So if we go view and we sort by date, we might get lucky, but it doesn't look like we're gonna get lucky here. Yeah, unfortunately, I'm not finding this. So we're just gonna search for this, right? We're gonna look for a burr.scad for a second, or actually, let's go git bash here. So let's do a git bash here, and let's do a grep. I haven't used grep in a while, so it might take me a while. Or it's not grep that I need to use. I need to use something else. I need to use the find command, right? So I want to like, so saying I want to grep for a file name is not the quite correct verbiage of what I'm trying to do here. So let's go over here. Let's say like this is what I want to look for, grep for file names. So this is kind of what I want to do, and should be somehow -L option. God damn it! So I have this as a shortcut, but it turns out that I don't know how to do that. So I'm going to make a grep for file name in my shortcuts. I'm gonna make this too, and I'm gonna go into my shortcuts really quick and go look for that. So grep for file name. So it's not really grep that I need to use. I think I need to do a find. Like, I think I need to use the find command, not the grep command. If anybody knows the correct bash code for that, that would be helpful. But I think I need to, like, search for file name bash. Let's try that. Find example bash. Excellent. So that actually got me something. So I'm going to go like this. Search for file name bash. And I'm just going to make another entry in my shortcuts, for example. Okay, so find example bash. And so find, okay, current folder, The name flag is going to be this. Okay, so that's all I got to do. So I'm going to take this, because I want to look for this, and I'm going to take the current example, and I'm just going to say search for burr.scad, right? Search for burr. So I'm just going to make this entry here, and I'm going to edit it, right? So I'm going to paste line, but I'm going to change this to burr.scad, and I hope this is a recursive search, but we'll find out. And I'm just going to take these notes here, and I want to edit some things here. So this commentary is wrong. We want to say use search for file name bash. So next time I look for that, I'm going to find it a little bit faster in my shortcuts. And then in my shortcuts down here, I want to just make a note of that, right? So next time I'm kind of looking for this and I haven't done a bash command for searching for a file name, I'll be able to find that a little bit faster. So now let's take this and see if that actually works. So see if that command will actually work in bash. So right here, we're inside of our models folder. We're just going to go right click and paste that and hope that it finds the folder. So okay, so it's in this folder right here. So I'm going to take that, and now I know that that was the model name, right? So it's so this right here, copy this, and we're going to paste it. So yeah, so that is the full place where this model is. So we're going to go find that model now, and we're going to see if I have a list of other things I worked on in here. So here's all the code for here. And hey, we can take a look and see what this is, right? So let's take a look and see what these designs are. So it's a slightly different design that kind of uses the same patent. But the idea was to make it so that the bolts didn't stick out, right? So we have these like little insets so that we would have to glue these parts together and make these out of wood. So this design would be made for wood rather than acrylic. And I like the design, but part of me thinks that it just looks too bulky, right? So the nice thing is we have these little ledges where we can kind of insert panels, but it looks a little bit too bulky for me. So I think that this is a good contender for making something, but right now, God, this GIF didn't quite work out very well. But right now, I think that this is going to be saved for later. This is a good contender, though. So this is a good contender for like a wood product. Let's go into the main file, the main SCAD file here, and see if we can find like an index of what I worked on here. So this is the file, this file regularized burr.scad. Hold on, let's make sure. Okay, summary. After making hack.scad, I think mechanically my concern is... Okay, so it looks like, even though okay. Oh, yep, here we go. We got like a little model history here. So let's take this model history, oldest to newest, and let's go into here and let's start kind of keep building this index. So burr.scad is right here, and it looks like this BBI, hack, and these things are older models. So let's take this list of other things I've worked on, and all we're trying to do is create a... we're trying to go through all the old code and look at those little crumbs of notes that tell me what the other things that I worked on were. Now, that kind of sucks that I don't have the actual the full names here, so we're going to have to go find those. So we know what the command is, so let's just go in here into the file system. Let's go right-click git bash here, and let's run that same search command and say we're going to do the find dot slash. So from the current folder, we're going to search for a name, and we're going to look for bbi.scad. So we're going to look for this. I don't think we have to quote that. I could be wrong. Yeah, so bolt bone infinity. So this is the full name. So let's take that, copy that. And that goes right here. Let's paste that in there. Oh, hold on. Copy. And paste that there. And, okay, we have that. So let's go in here and make sure that this list doesn't show us anything else. Like maybe there's the possibility we built these lists wrong, but let's go in here and open with Notepad++, see what the previous models are here. So let's just take this list as well, and let's go use this and say, okay, well, there's this thing right here, this BBI, then there's hack, and then there's hagger, and there's hag. So that looks pretty good. So let's just go open up hack now. So let's go find out what hack is. So go back, and we're going to do a git bash here, and we're going to do a look for find dot slash the name, and the name is going to be hack.scad. So hack.scad. Okay, let's go look for that. So it's just in a folder literally called hack, which is, I guess at some point in time I just didn't abbreviate it. So it's just hack/hack.scad. And I think that some of my older models, I didn't use this naming convention of, you know, a very verbose folder name, and then the file name is kind of an abbreviation. So let's go look for Hagger now. So let's go find /name and find Hagger.scad. Okay, and okay, so Hagger.scad. So it's in a folder called Hagger. So yeah, I kind of didn't abbreviate it previously. Okay, so let's go look for hag and then find /name and look for hag.scad. Okay, so it's also in a folder called hag. Okay, so my concern right now is that I want to make another file for like cutting washers out of felt, and I know it comes somewhere after here, but I'm kind of concerned that let's save this. Let's save this as like in models. Let's go models, and let's just call this index. So let's just call it 00dex dot underscore. So that way, you know, put the zeros there just as a hack to make sure this file kind of shows up first in the file system. And I don't know if Tetra spline block was the last thing I worked on or not, but let's go look at some of the pictures, right? So I usually put pictures in the file to make sure that I put pictures in the file to make sure that I don't have to render the code. I don't have to run the code to see what was in there. Right? I can just open up the pictures and see what's there. So we can see this design is kind of bigger than one of the other things I worked on. And I remember that the idea was, oh, I want to make things bigger quicker with these modular parts. The problem with making things bigger quicker is that the designs you end up with kind of end up looking kind of like, I don't know, it looks more juvenile to me than the other designs. Also, this design is a little bit harder to make because you'll see that the lighter colors are disembodied, right? So this light yellow here is disembodied from this light yellow. This light yellow is disembodied from here. So we have to have considerations for how we're going to manufacture this, right? So this is going to be harder to manufacture, and I don't think it looks as good. So I'm not gonna work on that, but that actually does look like one of the last things I worked on. And if we go into here, right, if we open this with Notepad++, we notice that we're pretty good in our. As we made more and more models, we started to get very consistent with always keeping like an index of the previous models, the current model, and the next model. So I'm going to say that this is actually up to date, and this is actually correct. And I'm going to say that the next model, right? So I'm going to make a little linked list here and say the next model is going to be it's going to be felt washers, right? So I guess they're felt washers for bolts, so I like to keep them as felt. Now, how do you spell felt? Is there a D in felt, or am I making that up? And just so feld. I think it's a DT. I don't know for sure. Felt. Maybe it's not. Why am I getting anime for felt? Okay, anyways, felt. Maybe it's just felt. Okay, so my bad. It's felt. It's not. There's no silent D in it. So bolt-blown felt washers. And this is going to be okay. Thank you, El Papa Pig. So yeah. So we're going to call this BFW. So BFW.scad. Right. That's the SCAD file we're going to use here to create this file. And we gotta. Yeah, anime for some reason. But we need to get this created really quick, because I need to get out of here at like 5:45. I'm going to have to... Well, it's 5:11. I have the reservation at 7. But we got to start coding, because we got to get something ready for that laser cutter. Because every single day we miss is a day we could have made some product, right? So this is what we're going to call it, right? So we're going to call it bolt-bone felt washers, so BFW. And then we're going to go into our master models folder, and we're just going to go file new and create another folder for another project, and that's what we're going to call it. And then in here, the first thing we want to do is we want to go go, just make a new text document. We're going to call it bfw.scad. And we just want to get something on screen working as quickly as possible. So the first thing we're going to do is we're just going to open up this in OpenSCAD. And we're going to put this over here on this side. That actually, if I have my console here, we don't really have much to see here. We'll worry about... We'll get used to moving this around as we go here. But okay, that's good. Let's put this index over here, and let's kind of rearrange how we're doing things. So we'll keep the code on this side. We'll keep the rendering on this side, or you know, maybe it makes more sense for the, like, if we want to really think about like if we don't want to be arbitrary about how we do things here, I guess it makes more sense for the code to be on the left and the rendering to be on the right, because I go left to right, and the rendering depends on the code, right? The code produces the rendering, so if we want to, I know this is really weird to be like that picky to say, I want a non-arbitrary reason for why I have this window on the left and why I have this window on the right? That's complete bonkers, but that's the way I do it. So, since whatever is rendered over here depends on the code on the left, and we're doing a workflow from left to right, top to bottom, we're going to keep it over here, right? So now we know that the model after this is going to be this not this thing. Let's close this. It's going to be, do I want to reload it? Yes, I want to reload this. Looks like I kind of closed the file. So let's go open it up. So it's called bolt bone something other felt washers here. So let's open this up. And this is the file we want to edit here. And so it's called bolt bone felt washers, right? / bfw.scad. And then we'll kind of like realign all this stuff here. So it looks like this is how I'm doing it. And we'll pretty this up later, but let's just get this running. So we have a complete blank slate. So what we're going to do? Well, we're going to do the usual constants 2020. So I haven't done this since 2020. So we have NFC 2020. We're going to use that same thing for the year 2021. So it's been pretty good for us so far. So what we're going to do here is in our shortcuts, NFC 2020, NFC 2020, and NFC-2020. We're going to just use this and say, oh, I did that totally wrong. NFC 2020. Okay, so 2021, right? The year is 2021. I'm just going to make this shortcut the same exact name, but it's going to be called 2021 in case I get the year wrong. And we're just going to say year 2020 can be used for year 2021, right? So I'm just saying that I'm going to bring these shortcuts forward. But anyway, so we're going to type NFC 2020 here. And we have a nice little snippet for kind of like how we arrange the code in our projects usually. So what's going on here is this is called No Framework Constants 2020. That's the name of the shortcut. So shortcut name is this, right? And we have where the shortcut begins is up here and the shortcut ends here. The style is a little bit different than the other code I've written. So 1 inch when exporting to Inkscape. So this is basically 1 inch when I'm laser cutting. And then the 1 inch variable actually needs to be different depending on what kind of machine I'm taking these blueprints to. So the ShopBot, the plasma cutter, and the laser cutter, we all need to configure the 1 inch variable to something different. And then after we've configured the 1 inch variable, we have some other variables that depend on it. So we have a lug. And a lug is a large graph paper unit. Why do I call it a lug? I don't know. That's just kind of like how it ended up being. So I've been doing it as lug for like 5 years. And it's just 1/4 of an inch. So the idea is to make everything snap to graph paper, so it's very easy to design on graph paper and then get it into a design really quick. So MMT is the model material thickness in lugs. SR, right, shaft radius. And BR is the bore radius. So there's shaft holes and there's bore radius holes for how I do things. There's also MUG, which stands for Meta Grid Unit. So if you notice on some of the designs, there's kind of like an implied grid that can emerge as you build with the design. So it's not always useful. but it is sometimes useful depending on the nature of the design. So if it's a bolt bone style model, which is then it is a useful abstraction. Now, hey, how's it going? I'm working on mechanical patents today. So yeah, mechanical patent break. Because I have to get to the shop soon. I have to get to the machine shop at us. Yeah. So yeah. So let's give you a quick rundown, right? So I'm in the middle of stuff, but I can give you a quick rundown of what that kind of looks like, right? Because you've never seen this. So let's just give you the quick rundown. I'm not going to explain it, but like on another day when I'm not like in such a rush, I'll give you a better explanation. But right now I've explained this too many times to too many people. So mechanical patent. This is a coffee table. It takes about a month, at least a month, to build this. There's going to be $450 of felt washers in this. So just the retail value of the washers that goes into this is going to cost $450, right? Because there's so many holes in here where it all gets bolted together. So I need to sell the final design for something in the thousands, right? So this is designed for a mold to cut. I want to water jet cut this mold out of steel and then pour molten aluminum into it, so that I can make these parts out of aluminum rather than acrylic. Right now, the first design is going to be made with acrylic. So these are a whole bunch of cutting plans. Yeah, the wood thing I showed you. Yeah, so you've kind of seen some of this stuff. Okay, yeah, you have seen some of this stuff. Cool. So I don't think I showed you like all of this stuff, but yeah, the wood thing here, right? This thing kind of here, and then you have room to put cords in here, so we can wire up the table and give the table like a. We could do like a LED tabletop if we wanted, right? That would be pretty awesome if the table kind of lit up and had electronics in it. And we have enough room to put wire here, wire here, wire here, and wire here. So that would be pretty awesome. Here's my little milk crate kind of design. And the milk crate takes like 1 to 2 weeks to make. So I can't really sell this cheaply. The milk crate itself takes $50 worth of material, and it takes 1 to 2 weeks to make. So let's go into here, and we're not going to need mug and air. These things... I'm going to keep this message here in my code. So this is not C code. This is you'll probably like this language. This is .scad code is code is code for drafting. Equals OpenSCAD, right? So OpenSCAD, right? So when we're talking about SCAD, we're talking about OpenSCAD code. The language is functional. So the language is designed. The syntax is imperative, but the language itself is functional, which is it throws you through some hoops. So there's some weird oddities to the language. It's not like really odd like JavaScript odd, but if you don't know that the syntax is functional, if you don't understand that the syntax is functional, you're going to get into some trouble. So yeah, because of this. Well, not all the code is going to be clear, but there is some clarity in the code. But anyways. Right, like I still have the same coding style, but the coding style I use for this may be slightly different. Because, right, it's a coding style that's designed to help me, like, I've made, like, a lot of projects. So, in this coding style, like, all these folders are different projects, right? These are all projects I've cut on the laser cutter. So I've actually done this quite a lot, and so therefore, the coding style has kind of evolved to facilitate rapid production of stuff. So, so the first thing we want is to just create like a cutting sheet. So we want to namespace this out. So we're going to say module. We're going to say module, and we're going to call it BFW. Right, BFW is the namespace, and it's going to be a cutting sheet. So we're going to say cutting sheet, and then we're going to call it. Let's just call it like 11 by. Technically, the sheets are like 11.75. but I think maybe just doing 11 by 11 might be fine. Let me think about it. Well, let's not waste material. Let's just do 1175 by 1175 washers. So we're trying to make some felt washers because felt washers are ridiculously expensive. So if we can start to cut some of our own, then we don't have to pay exorbitant prices. So we have this cutting sheet we want. And we also know that we need a module BFW a component. So we want a single component, and it's going to be called a this is going to be called a washer, right? So it's going to be a washer. And okay, so we got a washer, and then inside here we're going to cut a whole bunch of washers on a 11.75 by 11.75 sheet. Okay, so now that we have this, we have to figure out what that's going to be. So we need to just create some circles, right? This is going to be pretty dead simple, right? We're going to create a circle. This is a my own circle command, and I create circles that are always centered. It doesn't have the weird comments, neither the prologue and epilogue macros, so it's like a breath of fresh air. Oh, got ya, yeah. Oh, yeah, there's none of that. Yeah, yeah, this language does not let me get that crazy. So we know that the shaft radius is roughly going to be this. We do know that this circle command, I believe, is in native units. So we have to take this circle radius and we have to multiply it by the lug unit to get native units. And then we want to do a difference. So we want to do, so let's say difference I1. See if we have a, let's just do union difference. Okay, so this might be a little bit more code than we need for what we're doing, but and also, so it's a common pattern in we're doing like Boolean logic. This is Boolean logic, and a very common pattern is to do this like union difference pattern, right? So what's going on here, and this is way more code than we actually need for this, but I just want to get something working quickly. So we're going to take this circle. This is the shaft radius. So we want to subtract this. This is where we composite the negative aspects, and here's where we're going to composite the positive aspects. And so the outer radius, I really don't know what we want. I think we want something like outer radius in lugs is going to equal the shaft radius plus like maybe a it's the outer radius, so maybe we want to add like 1 lug divided by 2, and that'll give us something decent. We want these washers to be kind of thin, and then we're going to just say that you know, we have outer radius in native units, and that equals the outer radius in lugs. Outer radius in lugs times lug gives us the native units, right? So with this outer radius in native units, we can use this to draw a circle. And so this is also native units, but we just didn't make a variable for it. So, you know, we could say, you know, shaft radius in native units equals SR times lug. Okay, and then we could take this here. So we want to make sure we don't lose track of what kind of yeah, so we're creating blueprints. We're creating SVG blueprints to feed into a laser cutter. So you'll see what this looks like pretty soon. But first of all, we have to go in here, and there's some common functions that I use, and rather than import like a common function file, like a common utility file, I know it's very hackish to do this, but we're gonna do like a paste scad funcs 2020. So SF 2020. So I'm gonna make a note of this. SF 2020 folder. So it's been since 2020 since that I've done this. So I want to say, you know, Since 2020, this shortcut is still good in year 2021. So this shortcut is still good for 2021. So I just want to make a note of that. So SF 2021, SF 2021. In case I type 2021, because now the year is 2021, I just want to make sure I don't lose track of this very useful shortcut. So SF 2021. And yeah, so I'm going to go put this on our monitor again. And we're just going to say SF. We're going to say SF 2021. Actually, wrong year. SF 2020. And so this is just a whole bunch of common functions that I use in most of my projects, right? So instead of doing an include, I could do an include, but we're just going to paste this in here because we use it quite often, and it should be enough to get us going, right? So we're going to take this and save this, and we're going to save it as _.fun._, right? So the naming convention there is just so that I can go in here, and we're going to create like an include section, right? So somewhere in here, we're going to do includes section. And in the include section, we're just going to, well, we're going to put our includes, right? So let's do that. So includes section. The nice thing about what I'm doing is it's going to be more relatable, right? It's not going to be as abstract as that crazy graphics engine stuff. Like, it's going to, like, make more sense. So we're going to do scad. It's been a while since I've coded this. It's been a year, so let's do scad include. And so includes don't have double quotes around them, right? So when you use multiple languages, the languages kind of mash together and confuse the hell out of you sometimes. So we just want to go in here and say we're going to include, I think I could do, I don't think that's right. That doesn't look right. Well, let's try, actually, no, I think that's right. So let's do, /_.fun._, right? So I believe that's how we want it to work. So it doesn't look like it's failing on me. Cool. So now we are going to just go into here, and we're going to say, we're going to call that module. So we don't have to worry about forward declarations in this code. So it's not like C code where I have to worry about that. So I can just call the function before it exists. So BFW component washer. So let's call that and see what that looks like. So, okay, we got our washer. That does not look correct. I wanted to make something a lot bigger. And I see that when I cut and pasted that code, there's a thing that says CBS use low-res circles. So we're going to have to add that in here into the configuration. So we're going to say, this was from a different namespace, right? So we're going to call this BFW use low-res circles. And we're going to call this, we're going to say 0, right? So we don't actually want to use low-resolution circles. We want to use the high-resolution circles. We're going to go in here, and we're going to look for anywhere we see CBS. We're going to replace it with the new namespace, right? So this is kind of hacky, but so BFW is our new namespace. So we're going to just go find next and be like, okay, that's going to be replaced, and then that's the only thing that needed to be changed. And then if we look at this, it still looks wrong, but at least we got rid of that warning, right? So now let's go look at the logic we did, because this is absolutely not correct. Oh, nice. Nice. Awesome. So by the way, RBSRBS is very good at C code, right? They write very sane C code, not like the kind of code I write. And they write it very cleanly and concisely. Like, I do not write concise code, but RBSRBS, they do actually write very concise, to the point code, which I don't. I don't do that, but they do. And so, right, they're very efficient with their time, with the way they write their code. Anyways, so let's go look at this. So this inner radius may or may not be correct. We don't know which radius is wrong. I'm going to say that... Oh, well, it's this. This is obviously wrong. We did a plus instead of a... We did a multiplication rather than a addition, right? So we want to just add a little bit of trim to this washer. So that was wrong. So let's save that. So this minus this. Hold on. This should be the outer, right? Or... Oh, this is the inner? No, hold on. I got this backwards. I got this completely backwards, and then I named everything wrong, too. What the hell? Oh, wait, hold on. I'm going wrong here. Hold on. Okay, so let's see what I'm doing wrong here. I'm doing something completely wrong here. Okay, so let's consolidate. Let's just visualize this for a second. Right? Let's just comment both of this out and say, okay, if we have this, this is the shaft radius. And the shaft radius doesn't need any offset at all, right? We just want a normal shaft radius, but it needs to be times lug because it's native units. Okay, that's why it's like that. Okay, so this, I know that this is correct. And then over here, we want something a little bit bigger. So we want like shaft radius, oh, I see. This says lug divided by half of a lug, but it's already in terms of lugs. Okay, there we go. So getting your units right can be kind of complicated sometimes. So this is our washer. This is the basic washer that I want to use, right? So it's just going to be enough washer to, it's enough washer to protect the, I want to protect the, yeah, so this is the final product, and if we want a cutting path, so this is the cutting path right here. So this is the cutting path we're using, right? So the red is the outline. That's the cutting path, and the blue is the interior, right? So this is the final cutting path for the washer design, right? It's dead simple, right? It's dead simple code, and now we just want to duplicate this into a cutting sheet, right? So we know this works already. We're going to comment that out, and then we're going to take this, and we're going to go down here. Here's our cutting sheet, and so let's just put one of them here right now. And then we're going to take this, and this is, we're going to call this, right? So we're going to take this, and we're going to put it up here, and we're going to call it, right? So we're going to go right there, and we're going to call it, and same thing, but now we want to duplicate this. So we should have a grid clone command. So let's go look into our source code. It's just been a while since I've done this, so I don't know the exact syntax. So let's go look at our functions file and do like a grid clone x should be what we need. Or actually, no, grid clone. What did I call it? Oh, gx and gy for grid clone x and grid clone y. So we have the number of elements, and then we have the padding between them. And is this automatically centered, or is it not automatically centered? This might not be automatically centered. Let's not worry about that yet. So let's go grid clone x, and we want like I don't know how many we need, right? So let's just try 10, and then the spacing between them is going to be however large this washer is here. So we're going to go into so we're going to create a section in here. And we're going to call this section non-standard constants. So non-standard constants. So because I cut and paste a lot of stuff when I'm making a new project, the constants here are like constants that I often use in every single project, and these are going to be non-standard constants that I'm going to use specifically for this project. And I am going to read your comment after I get to this. So for here, we have this kind of hard-coded in here, outer radius in lugs. And so we're going to take this and say washer, we're going to say BFW washer outer radius, right? So that's what that is. And then we'll go up here and we'll say, you know, BFW washer outer radius equals. And so this is the basic math for getting this to work. And now that's in there. And we just kind of refactored that because now we want, what did we screw up here? BFD, oh, we were in the middle of this. So let's go over here and try not to break our code. So right here, we're going to say we want to clone this on the X. So let's clone it. Okay, so now we've cloned it, but we can see that we've made a problem here. And that's because we want to keep all of our constants in terms of our lug unit, which is not native units. So all constants below in terms of... Actually, I don't know if I can do this kind of commentary. I'm just going to keep it safe for now and do this kind of comment. All constants below in terms of lug unit, unless otherwise mentioned. So with data normalization, we really need to use some type of common unit that we use everywhere, and not get too much mixing and matching of our units. Otherwise, it'll make the code just ridiculously hard to follow, because we'll have like a whole bunch of like conversion adapter code, and we really don't want that. So this command gx is actually takes native units, so we have to times this by the lug unit to turn this into native units. Now, if we do that, we see, okay, we're a little bit closer, but we spaced by the radius. We at least need to space by the radius times 2, right? So, so let's say, let's call this SPC, right? This is the space amount. And we're going to take this, and we're going to times it by lug, we'll times this by 2, right? So this is the radius times 2 equals the diameter, right? So pretty simple, straightforward, right? And then we want to probably add a little bit of padding, right? So we might want to add, like, well, let's not worry about padding yet. Let's just get this working, right? So let's take, this is our spacing, and let's keep the spacing in terms of native units. So let's get rid of this. Let's keep the spacing, so let's call it spacing between parts in lugs. Okay, so let's take this right here, let's put it over here, and somewhere we have screwed up because this needs to be lug here. Okay, cool. So now we have this kind of like spaced out here, but it's not centered or anything, right? Yeah, completely. Well, I'm actually, my unit called lug is lug is... Yeah, so lug is my made-up unit, but I am doing things in Imperial, so I do think that, actually, let me read your other comments while we're here. So I already answered this, right? So final product. You then define the input block, and the thing calculates cutting pattern to make it, or you have to manually define movements. No, I'm not going to, no manual definitions. We're going to take the paths, and we're going to compile them into G-code, but that's all automated. We don't have to worry about that. So TIL, I don't know what TIL stands for. TIL? Oh, yeah, so... Yep, nope, it's not a... Coincidental, but no, this is completely coincidental. Yep, nope, that's just completely coincidental, but that's interesting. So I'm going to put that in my notes. Lug Wikipedia. Yeah, that's not what this is. It's an abbreviation for a large graph paper unit. Because it's a... So the idea is to be able to quickly go from graph paper to final code. I find that if I do the units in terms of graph paper, it just makes it easier for my design pipeline. So we have this here. Let's duplicate this. So we want to clone on both the Y, X, and Y, right? So if we do this... we have like a nice little array, but we need to center this, right? So I do have like a version of this command that would center it. So let's go look and see if we can find grid clone centered. Grid clone centered. Nope. Grid clone centered. GC centered. Clone centered. Centered. So I have no clue where this is. SCAD clone centered. So I have no clue where this is, so we're just going to have to... what we could do is we could look at some of our old code and see if we have that somewhere. But right now we're just going to say we don't know what this is yet. I know I have a shortcut for this, but I just can't find it. So we're just going to have to go to the end of the line and say to do find this. So I think it should be like GCX, GCY is what it should be called. And I don't know where it is, so we're just going to look in our shortcuts really quick. We're going to look in our functions file and make sure we don't have a thing called GCX, right? That would be what it would be called. Yeah, so we could also look into our other code here. So let's go look at create box shelves and look at the functions file. So the functions file right here, we might actually find like a GCX, GCY. So GCX. How about centered? Okay, I don't know where that is. We can't waste time here. I have to get this ready to cut today. So we're going to just gonna deal with it as it is. So we're just gonna say GXGY, and then to center this, we need to know. God, this sucks though. Well, we have the spacing between the parts. Well, if I reserve money. Yeah, so the machine shop costs money to rent, right? So if I miss a day, I'm wasting money, right? So let's just take this and say, well, we know the spacing, and we need to take the spacing, but it's the spacing minus 1, right? Because so if we do like the number of elements equals 10, right now. So right here we're going to say number of elements. And now that we have this number of elements, to center this, we need to do something like translate on x, or actually let's translate in lugs, and we need to translate by number of elements minus 1 times the lug spacing. And if we do that, if that formula is correct, then we're going to have the correct let's call this variable. Let's call this variable here. Let's call this center x equals this, right? And then center y is actually the same thing, right? So center x and center y, and we're going to go 0 minus center x, right? And we take that, and we screw that up because we need to take like half the number of elements, right? So we have to take half the number of elements minus 1. So let's go number of elements divided by 2 minus 1. And it looks like we're not quite centered. So 1, 2, 3, 4. 1, 2, 3, 4, 5. So it looks like I was off. So let's just remove this minus 1, say minus 0, and then see if that looks centered. 1, 2, 3, 4, 5. 1, 2, 3, 4. So we're still off. So let's just do this. Plus so it looks like minus 1 plus lug SPC divided by 2. This isn't the best formula here. This is a hackish formula, but we're just going to throw it together and get it working, right? So there we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So, okay. So, yes, I'm actually cutting washers. Yes, no joke. If I buy them, it will cost me... Yeah, if I actually buy these, it's going to cost me $450. Felt washers are actually very expensive. So, so we're going to translate on the X and then translate on the Y. So it's nice that I'm doing something kind of simple, right? Because I do more complicated things, but you've never seen this kind of code before. So there we go. Yeah, now if you can find me a place where I can buy felt washers in bulk, let me know. But for now, it's just going to be cheaper to cut them because they are very expensive, right? Like, go check on Amazon and see how much felt washers cost. It's ridiculous. Okay, so we got this, right? And so we can preview our cutting path, right? So we can render the cutting path. We still have some problems where there's these tangencies, so the washers aren't going to be, yeah, so, yeah, the material. Using cheap. A low. Yeah, it might be like a low demand product for some reason. But yeah, so we have this here. And the next thing we want to do is we want to create like a bounds, right? So we want to know what the bounds of this is, and we're going to really just hackishly figure out what the bounds are. So we're just going to do like an inch bound. So we're going to go inch bound and do 11.75 by 11.75. And then we're just going to say, we're just going to put nothing in here in this last parameter. I'll show you what that is for later. But if we do this, we can see that if we want 11 by 7.5 by 11.75, we have a lot more room to cut a lot more washers, right? So we're taking a pretty bold step here, right? So we're gonna be pretty confident and say I'm pretty confident that this is the correct size of washer I want, right? So no weird numbers in here, right? For the washer, it's just we're taking the outer radius is just, you know, the radius, the shaft radius, and then we're just going to add half of a lug. Yeah, that makes sense. So you know, with graph paper, where you have inch-based graph paper, the border of this is basically going to be like one graph paper cell in thickness. Yeah, maybe. I have no clue. Or maybe not the weight cost, the volume cost, maybe. Okay. But yeah, so let's go add more washers, right? So we know 10 is not enough. If we go crank that up to 20, right? Crank that up to 20, and we're almost there. It looks like maybe 1, 2, 1, 2, maybe like 24 is enough. So let's go pump that up to 24. And then we have like an array of washers that we're gonna like, okay, so 24 is not enough. Hey look, we're gonna keep with the conspiracy and use 23, right? Excellent. So 23 by 23. So we got this nice little thing. So now once we have this inch bounds is actually going to be cut as well, right? So some of the things we're going to do in our pipeline are going to be kind of hacky just so that we can get things working, right? So the end goal is just to get the machine to cut out what I want to cut out. And we want to make sure that we have a little bit of geometry on the upper and lower bounds so that the bounding box is perfect. We need a perfect bounding box so that the pipeline I use, everything just works out nicely. So what we're going to do in here is we're going to say PT for point. And now we're just going to cut like little squares. So instead of cutting that big rectangle, we're just going to cut a little square right here and a little square on all of the bounds. So this is this will be cut out of felt. Oh, got it, yeah. I forgot. Okay, let's go look that up for you really quick. So, felt washers. And go find them on Amazon. So, so felt washers, right? This is a felt washer, right? So this is the material. We want to make a washer out of this material. And the reason why we're making it out of this material is to protect the table. We don't want the bolts to destroy the material. We don't want to scuff up the material as we bolt this together. So this stuff is ridiculously expensive if you want to buy your own, right? It's expensive. So I might actually try to sell my own. Like, if I'm going to cut these, I might want to actually sell these as well. But right now, we got our cutting sheet, right? So now that we have this cutting sheet, it is almost 6 o'clock. I have this appointment at 7. So we gotta get moving on this. So let's full screen this, and because we have so many polygons, this actually takes a lot of effort to rotate until we yeah, probably because I was talking about metal earlier. I like sometimes I do the thing. I have like metal, wood, and plastic, so it depends on what I'm doing. But yeah, we're gonna use this. The kerf of the laser, right? The kerf of the laser this tangency shouldn't be too much of a problem, because the laser itself, this is the tool path here, and the laser is pretty thin, so we're not worrying about like off by 1 errors here, right? We're like, this is good enough, right? The laser has a little bit of kerf. We're not going to account for the kerf in our calculations. This tangents itself, but this is going to be material that ends up getting blasted away anyways. So this should be good. This should be good for what we need. Yeah, so yeah, it's a little bit very minor. Laser cutter slices very thin. Yeah, very thinner. So low kerf, not enough to worry about when making furniture scale product. Yeah, it's not enough to worry about for furniture scale product. If we were trying to make like smaller products, we would have to worry about that, but for this, we don't have to. So let's go, I haven't saved anything with this in a while, so I gotta put this on a new screen, and I'm gonna be paranoid, so I'm just gonna go over I'm just going to go over to my title screen thing for a second, or actually... Okay, I'll show you what I'm up to here. So, if we go over here, we're going to go File, we're going to go Export, and then we're going to go SVG. And, yeah, that was yesterday, but I just used that to black out the screen. So, in here, we're just going to make a new folder. So, so I don't know why this software does this for my right-click in here. I have no clue why that's wrong. We actually have to go into the file system, and we got to go, what was it called? It's called bolt bones something or other. So, god damn it. I don't even know what folder I'm in. Okay, hold on. Full file path to clipboard. Go over here. Paste that. Okay, so in here we're going to make a folder called Cut. And inside of Cut is where we're going to put all the stuff that gets cut, right? So Cut. And then in Cut, we're going to export this to the Cut folder. So here we're going to export this to the Cut folder. We're going to call this like a 1175 by 1175. So in inches, right? The laser cutter is only 12 feet by 12 feet. So I think I'm smart enough to know that 1175 is, you know, inches, 11.75. So we'll just call it that, .svg. And the next thing we want to do is we don't want to have to rerun this code. We could, in the far future, like months from now, we could accidentally break this code somehow. Or we just don't want to, when we're trying to search for something, we might want to just be able to have a quick preview of what we're looking at here. So we're going to take this, and we are going to just do a rectangular selection here, and make this, we're going to file, save this. We're going to save this, the superior metric system. Well, the metric system is very easy for conversions. Like, yes, it has the plus with conversions. However, the imperial system is very good with divisibility, right? So think about how many different ways you can divide 12, right? Versus how many ways can you evenly divide 12, right? Nah, it's garbage. All right. So let's go into actually, let's go paste. We might actually still have that on the clipboard. No dice. So let's go upat folder. So upat folder. Okay, and then let's go look for the bolt bone felt washers. So here's this, and then within here we're just going to say 1125 by 1125. Or actually, what I do like to do is .png. Well, let's not worry about naming conventions. So it's been a while since I've done this, so some of my naming conventions are not quite up to snuff because I just don't remember what the hell I was doing. So I need to go upstairs really quick because my girlfriend stole my flash drive a while ago, and I'm going to need that flash drive for... Actually, no, I have another flash drive down here. I got to get that flash drive because I got to, like, put it on the flash drive, get it ready to bring to the shop. So I gotta go do that. Flash drive. Flash drive, where are you? There you are. Okay, now I gotta find a place to plug this in. God, it's been such a while. Where am I gonna plug this in? Oh, we have this. I guess we could use this. Yeah? There we go. Okay. So, got that plugged in. And we have a Git repo here. So what we want to do is we just want to commit the current changes we have and get it ready for the shops, right? So we got this file ready for the shop, and we just want to commit what we've done so far in our UP stands for utility patent, right? So this is the utility patent repo. We're just going to go git bash here, and we're going to do a git status and a git add dot, and then git commit dash am, just get to the shop. Washers. Okay, so they're felt washers for the coffee table. Git status, git push github master. Let's go push this up to GitHub, because we have a very convoluted work process here. We're actually going to push it all the way up to GitHub, and then we're gonna download it off of GitHub to get it on a thumb drive. So we're going to go all the way to some servers across the world to put this up there, right? To get it on my flash, it's kind of crazy, right? To get this on my flash drive, I'm going to commit it to GitHub, put it somewhere like way across the world, and then I'm going to open up this other folder and download it from somewhere across the world just to get it from one place to the other where I currently am. I find that totally bizarre, but that's the reality. They only give you... I do. Yeah, I do have MakerWorks today. That's what we're doing. We're trying to get going. So utility patent. Let's go in here. Let's do a git bash here, and hope we didn't make any changes that we haven't committed yet. So git status. Oh, great. Are we gonna have merge conflicts? Well, those are PDFs and SVGs. We don't have too much problems. So let's do a git add dot or a. Do you want to do a git add or do you want to do like a git pull? I don't know. Let's do a git pull. Okay. And then we'll do a git push, and we just gotta get these two things synced up here. Okay. Git add dot. Okay, git status. Git commit dash am. I don't remember, my friend. Looks like box stuff. So I don't exactly remember what this was. I think it was MakerWorks is the machine shop. Okay, so now that we have that, let's do git push GitHub. Oh, it's just called origin. Okay, so makerspace is still kind of a vague kind of thing, but yeah, makerspace is the best way to call this. Okay, so we got that pushed up to GitHub. We have like 30 minutes. We have 30 minutes where we could kind of get something going, but the thing is that if I were to use the laser cutter for all the time for making the other things, I don't have enough time to get some other files ready, because I really need to also cut material on the table saw. 789. 789. I really should have got there earlier, because then I could cut material. So actually, if I get there now, I might be able to cut some material to prep some material for tomorrow. So I'm going to have to... Yeah, I'm doing the felt today. So is that felt upstairs? Yeah. So... Okay. So I gotta get going here. But before I get going, I want to make sure my repos are synced, right? Because I had those PDF files. So git status, git pull, GitHub. So I want to make sure that everything's synced up. So right now everything's not completely synced up. So git status. Okay, everything's synced up. So everything's synced up. I'm ready to go. But yeah, sorry, I gotta go, cause yeah, yeah. So yeah, yeah, later. So I'll still be doing like engine stuff, but it's gonna be a lot of like engine stuff and patent stuff, because my patent was granted. Like I actually have the patent for what I'm working on. So I just need to start trying to figure out how to make money off of this. So I think yeah. So I'll see you later. CRBS and El Papa Pig. Thanks for kind of viewing what I'm up to. And yeah, so I'll try to figure out a better format for how I do things, but right now, engine coding and I'm making coffee tables and rendering engines. Kind of weird, but alright, that's what I do. Okay, so later.